Subscribe to the channel so you don't miss out on any of these videos. The faint whispers of the universe's story aren't in its stars, but in the light we can barely see. There's a glow, almost hidden, in the cosmic infrared background, and this glow isn't just random heat. It's the echo of something extraordinary, the birth and formation of stars and galaxies billions of years ago. Imagine being able to glimpse the earliest building blocks of the universe, not by traveling through space, but by decoding light that has journeyed for eons. This light, faint and stretched by time, holds secrets about how the cosmos began shaping itself into the structure we see today. What if I told you that buried within this faint glow are answers to questions about our cosmic origins, answers that scientists are still unraveling? This isn't just about telescopes or data. This is about uncovering the hidden stories of ancient galaxies. Galaxies that burned brightly when the universe was young but have long since faded into obscurity. And yet, their story is still told through the heat they left behind. The cosmic infrared background is like finding a treasure map to the universe's past. But this map isn't clear or straightforward. It's scattered, dim, and layered with clues from billions of years ago. Understanding it is like piecing together a puzzle where half the pieces are missing, but each new piece reveals something breathtaking about our universe. To truly appreciate why this faint infrared light matters, we have to go back, not just to when stars first formed, but to when the universe itself was just a fraction of a second old. After the Big Bang, the universe was a chaotic, unimaginably hot place. As it expanded and cooled, the first atoms began to form, eventually clumping together to create the first stars. These stars weren't like the stars we see today. They were massive, short-lived, and incredibly bright. Their light traveled outward, interacting with gas, dust, and the fabric of the universe itself. Over time, this light became stretched, or redshifted, by the expansion of the universe, shifting into the infrared spectrum. Fast forward billions of years to today. That faint glow from those ancient stars still lingers, stretched into the infrared spectrum by the universe's constant expansion. It's not just coming from one place, it's everywhere, a background hum of heat that pervades the cosmos. This is what scientists call the cosmic infrared background, and it's a key to understanding how galaxies formed and evolved over billions of years. But detecting this glow isn't easy. It's incredibly faint, overshadowed by the brightness of nearby stars, planets, and even our own galaxy. It's like trying to hear a whisper in a crowded room. Scientists have had to develop incredibly sensitive instruments, like those aboard the Spitzer Space Telescope and the James Webb Space Telescope, to even begin to measure it. These tools allow us to see through the cosmic fog of dust and gas, revealing the ancient light that tells the story of star formation in the early universe. What makes the cosmic infrared background so fascinating is that it doesn't just tell us about individual stars or galaxies. It provides a panoramic view of the universe's history. Each photon of infrared light is like a time capsule, carrying information about the conditions in the universe at the time it was emitted. By studying this light, scientists can reconstruct the processes that led to the formation of the first galaxies, the growth of massive black holes, and the distribution of dark matter, the invisible scaffolding that holds the universe together. One of the most exciting discoveries tied to the cosmic infrared background is the realization that much of the star formation in the early universe was hidden from view. In the early stages of galaxy formation, stars were often shrouded in thick clouds of gas and dust, which absorbed their visible light. However, this dust also re-radiated the absorbed energy as infrared light, contributing to the cosmic infrared background. This means that by studying the infrared glow, we can uncover hidden star formation that wouldn't be visible in other wavelengths. The cosmic infrared background also helps us understand the large-scale structure of the universe. Galaxies aren't scattered randomly. They're arranged in a vast cosmic web, with clusters, filaments, and voids. The distribution of infrared light provides clues about how this structure formed and evolved over time. For instance, areas with brighter infrared emissions often correspond to regions of intense star formation and galaxy growth. By mapping the cosmic infrared background, scientists can trace the flow of matter through the universe and identify the regions where galaxies first began to form. But the cosmic infrared background isn't just about the past. It also has implications for the future. Understanding the processes that shaped the early universe can help us predict how galaxies, stars, and even planetary systems like our own will evolve. It's a reminder that the universe is a dynamic, ever-changing place, and that even the faintest light can have profound stories to tell. And here's the most mind-bending part. The cosmic infrared background might not just be telling us about stars and galaxies. Some scientists believe it could also hold clues about exotic phenomena, like the nature of dark matter or the existence of other universes. The more we study this faint glow, the more questions it raises. It's as if the universe is offering us a glimpse of its secrets, but only if we're willing to look closely and think deeply. So the next time you look up at the night sky, remember this: the stars you see are just the tip of the iceberg. Beyond them lies a vast, hidden story, written in faint infrared light, waiting to be uncovered. The cosmic infrared background is more than just a scientific curiosity. It's a testament to the universe's ability to surprise us, challenge us, and inspire us to keep searching for answers. And in that search, we might just discover not only where we came from, but where we're headed. The cosmic infrared background is a gateway to understanding not just the stars and galaxies that populate the universe, but the intricate tapestry of processes that brought them into existence. To truly grasp its significance, let's delve deeper into how scientists study this faint glow, the tools they use, and the profound insights it provides into the cosmos. When we observe the night sky with our naked eyes, we're limited to the visible spectrum, the rainbow of light our eyes can detect. However, most of the universe's story is written in wavelengths far beyond what we can see. The cosmic infrared background resides in one of these hidden realms, requiring specialized instruments to detect and study it. This is where space telescopes like Spitzer and James Webb come into play. The Spitzer Space Telescope, launched in 2003, was one of the first instruments designed specifically to observe the universe in the infrared spectrum. Orbiting far from Earth, it avoided the heat and infrared radiation emitted by our planet, allowing it to detect the faint glow of distant objects. Spitzer's observations of the cosmic infrared background revealed a patchwork of light from countless ancient galaxies, many of which were previously invisible. It was like turning on a flashlight in a pitch-dark room, illuminating a universe teeming with hidden activity. Then came the James Webb Space Telescope, JWST, a revolutionary leap forward in our ability to study infrared light. JWST's instruments are so sensitive that they can detect the heat of a bumblebee from the distance of the moon. With this unprecedented capability, JWST has been able to peer even further back in time, capturing light from galaxies that formed less than 1 billion years after the Big Bang. Its observations have provided a sharper and more detailed view of the cosmic infrared background, helping scientists uncover the earliest stages of galaxy formation. But why does this faint glow matter so much? The cosmic infrared background is like a fossil record of the universe's star-forming activity. By analyzing it, scientists can determine when and where stars formed in the early universe. This is done through a process called spectroscopy, which involves breaking down light into its component wavelengths. Each type of atom and molecule leaves a unique fingerprint in the light it emits or absorbs. By studying these fingerprints in the cosmic infrared background, scientists can identify the chemical composition, temperature, and motion of the star-forming regions that contributed to this glow. One of the most fascinating discoveries enabled by the study of the cosmic infrared background is the realization that the early universe was much more active than previously thought. During a period known as the cosmic high noon, roughly 10 billion years ago, galaxies were forming stars at an astonishing rate, far faster than they do today. This intense activity was largely hidden from view in other wavelengths, as the star-forming regions were shrouded in dense clouds of gas and dust. The cosmic infrared background, however, reveals this hidden activity, showing that the universe was a bustling workshop of star and galaxy formation. This realization has profound implications for our understanding of galaxy evolution. Today, most galaxies, including our own Milky Way, form stars at a relatively modest pace. But the cosmic infrared background tells us that this wasn't always the case. By studying this glow, scientists have been able to piece together a timeline of star formation, showing how galaxies transitioned from their early, chaotic phases to the more stable and structured forms we see today. Another key insight from the cosmic infrared background is its connection to dark matter. Dark matter, an invisible substance that makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it incredibly difficult to detect directly. However, it does interact with regular matter through gravity, influencing the formation and distribution of galaxies. By mapping the cosmic infrared background, scientists can trace the distribution of star-forming regions and, by extension, the underlying dark matter that shaped them. This provides a unique window into the role dark matter played in the early universe. But the cosmic infrared background isn't just a tool for understanding the past, it also challenges our current theories about the universe. For example, the amount of infrared light detected in certain regions doesn't always match predictions based on visible galaxies alone. This discrepancy has led some scientists to propose the existence of hidden populations of galaxies that are exceptionally faint or obscured. These galaxies could represent an entirely new class of objects, shedding light on aspects of the universe we've never considered. The study of the cosmic infrared background also has implications for understanding the role of black holes in galaxy evolution. In the early universe, many galaxies hosted supermassive black holes that grew rapidly by consuming surrounding gas and dust. This process, known as accretion, generates enormous amounts of energy, much of which is released as infrared light. By analyzing the cosmic infrared background, scientists can estimate the contribution of black holes to the overall energy budget of the universe and better understand their impact on their host galaxies. Perhaps one of the most tantalizing aspects of the cosmic infrared background is its potential connection to the cosmic dawn, the period when the first stars and galaxies began to form. These early objects were incredibly faint and distant, making them difficult to study directly. However, their collective light contributes to the cosmic infrared background, providing indirect evidence of their existence. By studying this light, scientists can gain insights into the properties of these first stars and galaxies, including their sizes, compositions, and lifespans. The cosmic infrared background is more than just a scientific curiosity. It's a reminder of how interconnected the universe is, with each galaxy, star, and black hole contributing to a cosmic symphony of light and energy. It challenges us to think beyond what we can see and to explore the hidden depths of the cosmos. And as our instruments and techniques continue to improve, the secrets of the cosmic infrared background will become even clearer, offering new insights into the origins and evolution of the universe. The cosmic infrared background, though faint and elusive, acts as a powerful thread connecting us to the earliest epochs of the universe. By continuing to examine its details, scientists are revealing answers to some of the most profound questions about cosmic evolution. However, its mysteries run even deeper, extending into areas where existing theories and observations sometimes clash, pushing the boundaries of our understanding. One of the most intriguing aspects of the cosmic infrared background is how it interacts with the larger framework of cosmology. This faint glow doesn't exist in isolation, it's intertwined with other components of the universe, including the cosmic microwave background, CMB, and the large-scale structure of matter. While the CMB is the afterglow of the Big Bang, representing the universe when it was just 380,000 years old, the cosmic infrared background paints a picture of a later era, dominated by the formation of stars and galaxies. By studying these two backgrounds together, scientists can create a more complete timeline of cosmic history. For instance, the cosmic infrared background can help refine our understanding of the Reionization era, a period when the first stars and galaxies reionized the hydrogen that filled the universe. This process transformed the universe from an opaque fog to the transparent expanse we see today. The faint infrared light from this era contains subtle clues about the timing and extent of reionization, offering insights into how the first light sources influenced their surroundings. What makes the cosmic infrared background particularly challenging and fascinating is the difficulty in separating its signal from other sources of infrared radiation. The universe is filled with noise, including the infrared light from stars and galaxies in our own Milky Way, as well as emissions from interstellar dust. Disentangling these foreground signals from the true cosmic infrared background requires sophisticated techniques and precise measurements. Scientists often rely on statistical analyses, combining data from multiple telescopes and surveys to extract the faint background signal. This task becomes even more complex when considering the role of gravitational lensing. Massive objects, like galaxy clusters, can bend and magnify the light from distant sources, creating distortions in the cosmic infrared background. While this effect can complicate measurements, it also provides a unique opportunity to study even fainter and more distant objects. Gravitational lensing acts as a natural cosmic magnifying glass, allowing us to peer further back in time and detect the contributions of ancient galaxies to the infrared glow. One particularly exciting avenue of research involves using the cosmic infrared background to study starburst galaxies, galaxies experiencing intense periods of star formation. These galaxies, often shrouded in thick clouds of dust, emit most of their light in the infrared spectrum. By analyzing the cosmic infrared background, scientists can estimate the cumulative impact of these galaxies on the early universe. This helps us understand how starburst activity influenced the growth of galaxies and the distribution of elements necessary for life. The cosmic infrared background also holds potential for uncovering primordial black holes, hypothetical black holes that may have formed shortly after the Big Bang. These black holes, if they exist, could have contributed to the infrared glow by accreting matter and releasing energy in the form of radiation. Detecting their subtle imprint on the cosmic infrared background would provide evidence for their existence and offer new insights into the conditions of the early universe. As our observational tools continue to improve, new discoveries about the cosmic infrared background are becoming possible. The Euclid Space Telescope, launched in recent years, is designed to map the large-scale structure of the universe with unprecedented precision. Although its primary focus is on dark matter and dark energy, its data will also contribute to our understanding of the cosmic infrared background, particularly in terms of its connection to galaxy clusters and the cosmic web. Another upcoming mission, the Nancy Grace Roman Space Telescope, will provide high-resolution infrared imaging and spectroscopy, enabling scientists to study the cosmic infrared background in even greater detail. By combining data from these telescopes with observations from ground-based facilities like the Atacama Large Millimeter/Submillimeter Array, ALMA, researchers can achieve a more comprehensive view of the processes shaping the universe. But perhaps the most transformative tool for studying the cosmic infrared background is the James Webb Space Telescope. Its ability to observe faint, distant objects in the infrared spectrum has already yielded groundbreaking discoveries about early galaxies and star formation. By targeting specific regions of the sky and analyzing their infrared emissions, JWST is helping scientists piece together the hidden history of the universe, revealing the interplay between stars, galaxies, and the cosmic web. Even as we uncover more about the cosmic infrared background, it continues to raise new questions. For example, what role did massive, early stars, often called population 3 stars, play in shaping this background? These stars, composed almost entirely of hydrogen and helium, are thought to have been incredibly bright and short-lived. Although none have been directly observed, their contributions to the cosmic infrared background could provide indirect evidence of their existence and properties. Another open question involves the relationship between the cosmic infrared background and cosmic voids, vast, empty regions of space where few galaxies exist. These voids can act as natural laboratories for studying the faintest components of the infrared glow, offering clues about the distribution of matter and energy on the largest scales. The cosmic infrared background also intersects with broader questions about the universe's fate. By understanding the processes that dominated the early universe, we can better predict how the universe will evolve over billions of years. Will star formation continue at a steady pace, or will the universe eventually run out of the raw materials needed to form new stars? The answers to these questions are encoded in the light of the cosmic infrared background, waiting to be uncovered. Ultimately, the cosmic infrared background reminds us of the interconnectedness of all things in the universe. It's a testament to the idea that even the faintest traces of light can carry profound stories about our origins. Each photon of infrared light is a messenger from the past, traveling billions of years to reach us and offering a glimpse into a time when the universe was a vastly different place. As we continue to study this faint glow, we are not only learning about the cosmos but also about ourselves, our place in a universe that is far more vast, intricate, and mysterious than we could ever have imagined. And with each new discovery, the cosmic infrared background invites us to look deeper, to question more, and to never stop seeking the answers hidden in the light of the stars. The exploration of the cosmic infrared background (CIB) goes beyond understanding the early universe. It delves into the very fabric of cosmic evolution, revealing how fundamental forces shape the galaxies, stars, and structures we see today. This faint glow, which has traveled billions of years to reach us, acts as a cosmic ledger, documenting the epochs of star formation, the role of dust, and the energetic processes that occurred in the infancy of the universe. But despite its richness in information, the CIB is one of the most elusive components of cosmic radiation, making its study as challenging as it is rewarding. One of the key insights provided by the cosmic infrared background is its role as a bridge between the cosmic microwave background (CMB) and the visible light we observe from modern galaxies. The CMB represents the universe in its earliest state, a snapshot of its infancy. Meanwhile, visible light emitted by galaxies today reflects the current state of the universe. The CIB fills in the gaps, representing the intermediate stages when stars and galaxies were forming at a rapid pace. This intermediate phase is critical for understanding how the universe transitioned from its hot, dense beginnings to the structured cosmos we inhabit today. A significant portion of the CIB signal comes from light emitted by stars that were later absorbed and re-emitted by interstellar dust. Dust plays a complex role in cosmic evolution. On one hand, it obscures our view of the stars that lie behind it, making certain regions of the universe difficult to study using visible light. On the other hand, dust acts as a secondary emitter, glowing in the infrared spectrum and providing indirect information about the stars and processes hidden within it. The cosmic infrared background is essentially the integrated light of countless such processes, spread across the universe. To study the CIB, scientists often focus on anisotropies, or small variations in its brightness across the sky. These variations provide clues about the distribution of galaxies and star-forming regions. By analyzing these patterns, researchers can trace the large-scale structure of the universe and identify regions where galaxies are clustered together or spread apart. These studies are closely tied to the study of dark matter and dark energy, the mysterious components that dominate the universe's mass-energy budget. Dark matter, which does not emit light, influences the distribution of galaxies and the cosmic infrared background. It forms the gravitational scaffolding upon which galaxies and clusters are built. By studying the CIB, scientists can indirectly map the distribution of dark matter, gaining insights into its properties and behavior. Meanwhile, dark energy, which drives the accelerated expansion of the universe, affects the overall evolution of the structures that contribute to the CIB. Understanding how these forces interact is crucial for building a comprehensive model of the cosmos. The cosmic infrared background also has implications for our understanding of cosmic star formation history. One of the key goals of astrophysics is to create a timeline of when and where stars formed throughout the universe's history. The CIB acts as a census of star formation, providing an integrated measure of all the light emitted by stars, both visible and obscured by dust. By comparing the CIB with other observations, such as those of individual galaxies or star clusters, scientists can refine their models of how stars formed and evolved over time. One of the most exciting discoveries in recent years has been the identification of ultra-distant galaxies that contribute to the cosmic infrared background. These galaxies, which formed less than 1 billion years after the Big Bang, are some of the earliest structures to emit light. Observing them directly is challenging due to their extreme faintness, but their cumulative light contributes to the CIB. Advanced telescopes like the James Webb Space Telescope, JWST, are now capable of detecting these faint sources, helping to unravel the details of their contribution to the infrared glow. However, the study of the cosmic infrared background is not without its controversies. One ongoing debate involves the extent to which the CIB is influenced by extragalactic sources versus sources within our own galaxy. While the majority of the CIB is thought to come from distant galaxies, some scientists argue that foreground sources, such as interstellar dust in the Milky Way, may also play a significant role. Separating these contributions requires careful modeling and precise measurements, a task that continues to challenge researchers. Another area of active research involves the potential connection between the cosmic infrared background and cosmic inflation, the rapid expansion of the universe that occurred shortly after the Big Bang. Some theories suggest that the CIB could carry subtle imprints of inflationary processes, encoded in its anisotropies. Detecting these signals would provide a direct link between the earliest moments of the universe and the later epochs of star formation and galaxy evolution. In addition to its scientific importance, the cosmic infrared background has philosophical implications. It serves as a reminder of the interconnectedness of cosmic events, showing how processes occurring billions of years ago continue to shape the universe today. Every photon of infrared light that reaches us represents a story of creation, destruction, and transformation, a testament to the dynamic and ever-changing nature of the cosmos. As technology advances, the study of the cosmic infrared background is entering a new era. Future missions, such as the planned Sphere-X spectrophotometer for the history of the universe, Epoch of Reionization, and ICE's Explorer, aim to conduct an all-sky survey of the infrared universe, providing unprecedented detail about the CIB and its sources. These missions will complement existing telescopes, offering new opportunities to explore the mysteries of the faint infrared glow. But even as we uncover more about the cosmic infrared background, its full story remains elusive. It is a puzzle with many missing pieces, each one representing a challenge for future generations of scientists. By continuing to study this enigmatic glow, we not only gain insights into the universe's past but also lay the groundwork for understanding its future. The cosmic infrared background is a silent witness to the universe's history, a faint echo of the light that once illuminated the first stars and galaxies. Its study is a journey into the unknown, a quest to uncover the hidden chapters of cosmic evolution. And as we delve deeper into its mysteries, we are reminded of the boundless curiosity that drives us to explore the cosmos, a curiosity that will continue to inspire new discoveries for generations to come. The cosmic infrared background, CIB, is not just a window into the past, it's a reflection of the universe's intricate interplay of energy, matter, and time. As we push forward with technology and innovation, we continue to reveal the hidden secrets encoded in this faint infrared glow. But the study of the CIB also reminds us of the limitations of our knowledge and the vastness of the unknown. Each new discovery leads to more questions, fueling our desire to understand the cosmos. One of the fascinating aspects of the CIB is its relationship with Reionization, a period in the universe's history that significantly shaped the structure and evolution of galaxies. After the Big Bang, the universe entered a phase known as the Dark Ages, during which neutral hydrogen dominated, and no significant light sources existed. The emergence of the first stars and galaxies, however, began to ionize this neutral hydrogen, marking the end of the Dark Ages. The CIB provides a unique perspective on this transformation, capturing the cumulative light from these first luminous objects. By analyzing the infrared background, researchers can infer the properties of the first stars, often referred to as population 3 stars. These stars were massive, short-lived, and composed almost entirely of hydrogen and helium, as heavier elements had not yet been formed. Their intense radiation played a crucial role in reionizing the universe, setting the stage for the formation of later generations of stars and galaxies. However, direct observation of these stars is nearly impossible due to their extreme distance and faintness. The CIB offers an indirect method of studying their properties and understanding their impact on the cosmos. Dust, a seemingly mundane component of the universe, plays a pivotal role in shaping the CIB. While it might obscure visible light, it also serves as a source of valuable information in the infrared spectrum. The study of dust emission in the CIB reveals details about the composition, temperature, and distribution of dust in early galaxies. This, in turn, provides insights into the processes of star formation, as dust is a byproduct of dying stars and serves as a building block for new star systems. By mapping the contribution of dust to the CIB, researchers can better understand the life cycle of matter in the universe. The cosmic infrared background also intersects with studies of gravitational lensing, a phenomenon in which the gravity of massive objects, such as galaxy clusters, bends and magnifies the light from background sources. Gravitational lensing provides a natural telescope for observing distant objects, allowing scientists to study the faint sources that contribute to the CIB. By combining observations of gravitationally lensed galaxies with measurements of the CIB, researchers can probe the distribution of dark matter and the large-scale structure of the universe. As we continue to study the CIB, one of the challenges lies in distinguishing its signal from other sources of infrared radiation. The interstellar medium, ISM, within our own galaxy emits infrared light, creating a foreground that can obscure the faint CIB signal. Advanced data processing techniques and models are required to separate these contributions, ensuring that the measurements of the CIB are accurate. These efforts highlight the complexity of studying the CIB and the importance of collaboration across disciplines in astrophysics. The cosmic infrared background also has a profound connection to the study of black holes, particularly supermassive black holes that reside at the centers of galaxies. As these black holes consume surrounding material, they release immense amounts of energy, much of which is absorbed and re-emitted by dust in the form of infrared light. This process contributes to the CIB, linking it to the growth and activity of black holes throughout cosmic history. By studying the CIB, researchers can gain insights into the role of black holes in galaxy evolution and their impact on the surrounding environment. The future of CIB research is bright, with planned missions and technological advancements poised to revolutionize our understanding of this mysterious glow. Instruments like the James Webb Space Telescope, JWST, are already providing unprecedented views of the infrared universe, allowing scientists to probe the earliest stages of galaxy formation with greater precision. Upcoming missions like SphereX aim to conduct comprehensive surveys of the infrared sky, mapping the distribution of light and identifying its sources in unparalleled detail. These efforts are complemented by ground-based observatories and collaborative projects that bring together data from multiple wavelengths. By integrating observations from the infrared, visible, and other parts of the electromagnetic spectrum, researchers can create a more complete picture of the universe's history and evolution. The study of the CIB is a testament to the power of innovation and collaboration in science, demonstrating how diverse approaches can come together to tackle some of the most profound questions in astrophysics. Beyond its scientific significance, the cosmic infrared background has a way of inspiring wonder and curiosity about the universe. It represents a cosmic narrative, a story of creation and transformation that has unfolded over billions of years. Every photon of light that contributes to the CIB is a reminder of the interconnectedness of cosmic events, from the formation of the first stars to the development of galaxies and the emergence of life. It's a story that continues to unfold, inviting us to explore, question, and discover. As we look to the future, the study of the CIB holds the promise of unlocking even more profound mysteries. It is a journey that requires patience, ingenuity, and a willingness to embrace the unknown. The cosmic infrared background is more than just a faint glow in the sky. It is a window into the soul of the universe, a reminder of the boundless potential of human curiosity and the infinite possibilities that lie ahead. The cosmic infrared background, CIB, continues to be a crucial element in decoding the mysteries of the universe, revealing intricate details about its earliest and most transformative epochs. What makes the CIB particularly compelling is its ability to encapsulate the light emitted during the most dynamic phases of star and galaxy formation. These processes have left behind a faint, yet omnipresent glow that acts as a cosmic fingerprint, giving us an indirect but powerful tool to understand our origins. The earliest galaxies that contributed to the CIB were vastly different from the galaxies we observe today. These primordial structures were smaller, more chaotic, and characterized by intense bursts of star formation. During these periods, the young universe was a hotbed of activity, with massive stars rapidly forming and expelling material that seeded future star systems. The CIB encodes this frenetic energy, allowing scientists to study the rate at which these early galaxies formed stars and the efficiency with which they converted gas into stellar populations. This faint glow also holds clues about the environment in which these first stars and galaxies emerged. During the early universe, conditions were starkly different from those today. The chemical composition was simpler, dominated by hydrogen and helium, as heavier elements, like carbon, oxygen, and iron, had not yet been synthesized through stellar nucleosynthesis. As massive stars burned through their nuclear fuel and exploded as supernovae, they enriched the surrounding interstellar medium with these heavier elements, initiating the cycle of chemical evolution that continues today. By studying the CIB, scientists can trace this chemical enrichment over cosmic time, gaining insights into how the elements that make up planets, and even life itself, came into existence. An essential aspect of the CIB is its connection to the large-scale structure of the universe. The faint infrared glow is not distributed evenly across the sky. Instead, it exhibits fluctuations that correspond to the clustering of galaxies and matter on a cosmic scale. These fluctuations, or anisotropies, provide a direct link to the distribution of dark matter, the mysterious substance that makes up the majority of the universe's mass. By mapping the anisotropies in the CIB, researchers can study how galaxies formed and evolved within the scaffolding of dark matter, revealing the interplay between visible and invisible components of the cosmos. Another fascinating dimension of the CIB is its role as a complementary probe to other cosmic phenomena, such as the cosmic microwave background, CMB. While the CMB captures the universe as it was approximately 380,000 years after the Big Bang, the CIB focuses on much later periods, providing a bridge between the early universe and its more mature stages. Together, these cosmic backgrounds offer a holistic view of the universe's evolution, from its infancy to the formation of complex structures. The potential of the CIB to uncover new physics cannot be overstated. As we refine our observational capabilities and develop more sophisticated models, the study of the CIB could lead to breakthroughs in understanding phenomena like dark energy, the force driving the accelerated expansion of the universe. The CIB's faint glow, influenced by gravitational lensing and the clustering of galaxies, holds subtle imprints that could help constrain the properties of dark energy and its impact on cosmic evolution. Despite its profound importance, the study of the CIB is not without its challenges. One of the most significant hurdles lies in separating the CIB signal from foreground emissions within our own galaxy. The Milky Way's interstellar dust, heated by starlight, emits infrared radiation that can mask the much fainter CIB. Advanced statistical techniques and machine learning algorithms are being developed to isolate the CIB, ensuring that the data collected is as accurate and uncontaminated as possible. Looking ahead, the future of CIB research is promising, thanks to technological advancements and ambitious missions. Projects like the James Webb Space Telescope, JWST, are already revolutionizing our ability to study the infrared universe, providing unprecedented resolution and sensitivity. The JWST, with its ability to peer through dust and observe the earliest galaxies, complements the study of the CIB by offering direct observations of the sources that contribute to this diffuse glow. Moreover, ground-based observatories, equipped with state-of-the-art detectors, are conducting surveys to map the infrared sky with remarkable precision. Collaborative efforts between these observatories and space-based telescopes are creating comprehensive datasets that enable cross-correlation studies, providing a more complete picture of the universe's history. Upcoming missions, such as the Euclid spacecraft and SphereX, are set to enhance our understanding of the CIB by conducting wide-field surveys and capturing the infrared emission from billions of galaxies. The CIB's potential extends beyond astrophysics, intersecting with other fields of science, such as cosmology and particle physics. For instance, the study of the CIB can shed light on the nature of primordial black holes, hypothetical objects that could have formed shortly after the Big Bang. These black holes, if they exist, would leave an imprint on the CIB through their interactions with surrounding matter, providing indirect evidence of their presence. Additionally, the CIB could offer clues about the nature of dark matter, particularly if it consists of exotic particles that interact with radiation in subtle ways. By examining the detailed properties of the CIB, scientists can test theories about dark matter candidates, such as weakly interacting massive particles, WIMPs, or axions, and their potential effects on the infrared background. At its core, the cosmic infrared background is a testament to the interconnectedness of cosmic phenomena. It links the physics of star formation, galaxy evolution, and large-scale structure to the fundamental forces that govern the universe. The faint glow of the CIB is a reminder of the countless stars and galaxies that came before us, each contributing its light to a tapestry that spans billions of years. As we stand on the cusp of a new era in astronomy, the study of the CIB will continue to illuminate the path forward, offering insights into the origins and destiny of the cosmos. It is a journey of discovery that speaks to the very essence of human curiosity, inspiring us to look up, explore, and wonder about the universe's deepest mysteries. The cosmic infrared background, CIB, serves as a silent witness to the most profound events in the universe's history, offering invaluable insights into the epochs that shaped the cosmos. As astronomers continue to unravel its mysteries, they also deepen our understanding of humanity's place in this vast and intricate universe. The glow we detect today is a relic of the universe's fiery youth, a whisper from a time when galaxies were just beginning to form, and the stars we now admire were still in their nascent stages. One of the most exciting aspects of studying the CIB is its potential to reveal the so-called hidden universe. This refers to regions of space obscured by thick clouds of gas and dust that block visible light but emit strongly in the infrared spectrum. Many of these regions harbor some of the most dramatic events in the cosmos, the birth of stars and the formation of massive galaxies. The dust, heated by the intense radiation from young stars, emits this heat in the form of infrared light, which contributes significantly to the CIB. By studying this emission, we gain a window into these otherwise invisible regions, shedding light on processes that would otherwise remain shrouded in mystery. The study of the CIB also intersects with another fascinating field of astrophysics, the search for the first stars and galaxies, often referred to as the cosmic dawn. These are the objects that formed when the universe was less than 1 billion years old. They played a crucial role in reionizing the universe, a process that transformed the cosmos from an opaque fog to the transparent state we observe today. The light from these first stars and galaxies, heavily redshifted by the expansion of the universe, contributes to the CIB, allowing researchers to indirectly study these elusive objects and the transformative era they represent. Furthermore, the CIB provides a means of probing the interplay between stars and the interstellar medium, ISM, the vast reservoir of gas and dust that pervades galaxies. The ISM is both a cradle and a grave for stars, as it supplies the material for star formation and receives the remnants of stars at the end of their lives. The interaction between stars and the ISM is a fundamental driver of galaxy evolution, and the CIB captures this dynamic process across cosmic time. By analyzing the spectral properties of the CIB, astronomers can disentangle the contributions from different types of stars and ISM environments, painting a detailed picture of how galaxies grow and change over billions of years. One of the most compelling tools for studying the CIB is the technique of cross-correlation, which involves comparing the CIB with other cosmic signals. For example, researchers can cross-correlate the CIB with maps of the cosmic microwave background, CMB, to study the gravitational lensing effect, where the gravity of massive structures distorts the path of light. This approach allows scientists to trace the distribution of matter, both visible and dark, providing insights into the large-scale structure of the universe and the forces shaping it. The study of the CIB also has implications for understanding the life cycle of galaxies. Galaxies are not static. They evolve through processes like mergers, interactions, and the accretion of gas. These processes drive bursts of star formation and feed supermassive black holes, which in turn emit copious amounts of energy that influence their host galaxies. The CIB captures the integrated light from these activities, offering a cumulative record of galaxy evolution over cosmic time. By studying this light, scientists can infer the history of star formation and black hole activity in the universe, providing context for the galaxies we see today. Another intriguing aspect of the CIB is its connection to the phenomenon of cosmic variance. This refers to the fact that the universe, while generally homogeneous on large scales, exhibits variations in the distribution of matter and energy. These variations are imprinted in the CIB as fluctuations in its intensity across different regions of the sky. By analyzing these fluctuations, researchers can test models of cosmic structure formation, refine measurements of fundamental cosmological parameters, and explore the initial conditions of the universe. The faint glow of the CIB is not just a relic of the past, it also serves as a benchmark for future discoveries. As observational techniques become more sophisticated, the sensitivity of infrared telescopes improves, allowing researchers to detect even fainter sources of light. These advances will enable the study of the most distant galaxies and the smallest contributions to the CIB, pushing the boundaries of what we know about the universe. For instance, the James Webb Space Telescope, JWST, has already begun to revolutionize our understanding of the infrared universe. Its unparalleled resolution and sensitivity allow it to observe individual galaxies that contribute to the CIB, providing direct measurements of their properties. By comparing these observations with the integrated light of the CIB, scientists can validate models of galaxy formation and evolution, ensuring that they accurately represent the processes shaping the cosmos. Additionally, new missions like SphereX are set to map the entire sky in the infrared, capturing the CIB with unprecedented detail. These maps will serve as a valuable resource for studying the connections between galaxies, dark matter, and the large-scale structure of the universe. They will also enable tests of exotic theories, such as the possibility of primordial black holes contributing to the CIB, or the effects of new physics beyond the standard model of cosmology. The cosmic infrared background, though faint and diffuse, is a treasure trove of information about the universe's history and its fundamental laws. It serves as a bridge between the earliest moments of cosmic creation and the complex structures we observe today, linking the physics of the Big Bang to the processes shaping galaxies and stars. As we continue to explore this enigmatic glow, we are not only uncovering the secrets of the cosmos but also deepening our appreciation for the intricate web of phenomena that define our universe. The cosmic infrared background, CIB, is a reminder of how much we have yet to learn about the universe and how interconnected everything truly is. Even faint whispers of light, originating billions of years ago, hold the power to unravel mysteries that continue to baffle astronomers. One particularly fascinating application of CIB research involves the exploration of dark matter and dark energy, two of the most perplexing components of the universe. Dark matter, which makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. However, its gravitational effects can be inferred from its influence on visible matter, radiation, and the large-scale structure of the universe. The CIB offers a unique way to study dark matter through the technique of gravitational lensing, where the light from distant galaxies or the CIB itself is bent and magnified by the gravitational pull of intervening dark matter. By mapping these distortions, researchers can trace the distribution of dark matter and better understand its role in cosmic evolution. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, can be probed using the CIB. The large-scale structure imprinted on the CIB provides a snapshot of how galaxies and galaxy clusters were distributed in the past. By comparing this distribution to current observations, scientists can study how cosmic structures have evolved over time and how dark energy has influenced this evolution. These studies contribute to refining models of the universe's expansion history and exploring alternative theories of gravity. The cosmic infrared background also holds clues about exotic astrophysical phenomena, such as primordial black holes, PBHs. These hypothetical black holes are thought to have formed in the early universe, long before stars and galaxies came into existence. Some theories suggest that PBHs could account for a portion of dark matter, as their gravitational pull would affect the distribution of light and matter. If PBHs exist, they might contribute faint infrared light to the CIB through interactions with surrounding matter, offering a potential avenue for their detection. Another intriguing aspect of CIB research involves the role of population 3 stars, the first generation of stars that formed after the Big Bang. These stars were composed almost entirely of hydrogen and helium, as heavier elements had not yet been forged in stellar interiors. Population 3 stars are thought to have been massive, short-lived, and incredibly bright, producing intense ultraviolet radiation. Over billions of years, this light has been redshifted into the infrared spectrum, contributing to the CIB. By studying the spectral properties of the CIB, astronomers hope to identify the fingerprints of these ancient stars and better understand their role in shaping the early universe. The CIB also provides a way to study the formation and growth of supermassive black holes, SMBHs, which reside at the centers of most galaxies. SMBHs are thought to have grown from smaller seed black holes formed during the collapse of massive stars or through the direct collapse of dense gas clouds. As SMBHs grow by accreting matter, they emit copious amounts of energy, some of which is reprocessed by surrounding gas and dust into the infrared spectrum. This reprocessed light contributes to the CIB, offering a window into the processes driving the growth of these cosmic giants and their impact on their host galaxies. Furthermore, the CIB can reveal information about cosmic feedback mechanisms, where energy from stars and black holes regulates the formation of new stars and the growth of galaxies. For instance, the intense radiation and winds from massive stars and SMBHs can heat or expel gas from galaxies, suppressing star formation. This feedback is a critical component of galaxy evolution, as it helps explain why galaxies like the Milky Way have relatively modest star formation rates despite having abundant gas. By studying the CIB, astronomers can trace the history of these feedback processes and their role in shaping the universe. The cosmic infrared background also intersects with the field of cosmic archaeology, which aims to reconstruct the history of the universe by studying its remnants. Just as archaeologists piece together the past from artifacts, astronomers use the CIB to infer the properties of ancient galaxies and star-forming regions. This approach has led to discoveries of so-called protoclusters, groups of galaxies in the early stages of formation that eventually evolve into massive galaxy clusters. These protoclusters are often obscured by dust, making them difficult to detect in visible light. However, their infrared emission contributes to the CIB, allowing researchers to identify and study these building blocks of cosmic structure. In recent years, advancements in machine learning and data analysis have revolutionized the study of the CIB. Complex algorithms can sift through vast datasets, identifying subtle patterns and correlations that would be impossible to discern manually. These techniques are particularly valuable for separating the CIB from foreground emissions, such as light from nearby stars and galaxies, which can obscure the faint signal of the CIB. By refining these methods, researchers can extract more detailed information about the origins and properties of the CIB, paving the way for new discoveries. The future of CIB research is incredibly promising, with upcoming missions poised to expand our understanding of the infrared universe. For example, the Nancy Grace Roman Space Telescope, set to launch in the coming years, will conduct wide-field infrared surveys that will provide unprecedented detail about the CIB. These surveys will complement observations from ground-based telescopes and other space missions, creating a comprehensive picture of the processes shaping the universe. Ultimately, the cosmic infrared background is a testament to the interconnectedness of cosmic phenomena. It encapsulates the light of countless stars and galaxies, weaving a narrative that spans billions of years. As we continue to explore its depths, we are not only uncovering the secrets of the universe but also forging a deeper connection to the cosmos, a reminder of our shared origins and the boundless potential of human curiosity. The study of the cosmic infrared background, CIB, is an ongoing journey into understanding the universe's formative years, revealing intricate details about its structure and evolution. One of the most exciting prospects is how the CIB serves as a bridge between observations of the past and predictions about the future. By piecing together this faint infrared light, astronomers can refine our understanding of cosmic history and even gain insights into the universe's ultimate fate. To appreciate the full scope of the CIB's significance, consider its role in addressing the cosmic star formation history. This is essentially a timeline of when and where stars formed throughout the universe's history. Scientists know that star formation peaked several billion years after the Big Bang during an era known as the cosmic noon, after which it gradually declined. The CIB is critical in mapping this timeline because it captures the light emitted by young, star-forming galaxies that are otherwise hidden by dust. By studying the CIB, astronomers can determine how much starlight was absorbed and re-emitted by dust, filling in gaps in our understanding of when and how stars and galaxies formed. But the CIB does more than just catalog star formation. It also provides clues about the assembly of large-scale cosmic structures, like galaxy clusters and the vast web of matter that permeates the universe. These structures began forming under the influence of gravity, starting as tiny fluctuations in the density of matter shortly after the Big Bang. The light captured in the CIB offers a snapshot of this process, showing how early star-forming regions evolved into the massive structures we see today. This kind of data helps refine simulations of cosmic evolution, making them more accurate and predictive. The CIB also connects us to one of the most profound questions in cosmology: how the interplay between visible matter, and dark energy shaped the universe. Dark matter's gravitational influence provided the scaffolding for galaxies and stars to form, while dark energy has been driving the universe's accelerated expansion. The distribution and intensity of the CIB can shed light on these dynamics, offering indirect evidence of how these unseen forces interact with the visible universe. Another frontier of CIB research involves detecting signals from the very first stars and galaxies. These primordial objects were vastly different from those we see today, as they lacked heavier elements like carbon, oxygen, and iron, which are produced in later generations of stars. The first stars, often referred to as population 3 stars, were massive, burned through their fuel quickly, and exploded in powerful supernovae. The light from these stars is thought to be redshifted into the infrared, making the CIB a potential treasure trove of information about this early epoch. Detecting these signals, however, is incredibly challenging. The light from the first stars is extremely faint and competes with emissions from galaxies and other cosmic sources. To isolate these signals, astronomers use a combination of techniques, including spectral analysis, which breaks down the CIB into its component wavelengths, and spatial correlation studies, which examine how the light is distributed across the sky. By combining data from multiple telescopes and missions, scientists hope to disentangle these signals and uncover the fingerprints of the universe's first stars. The cosmic infrared background also opens doors to studying cosmic reionization, another key phase in the universe's history. After the Big Bang, the universe was initially hot and dense but gradually cooled, allowing neutral hydrogen atoms to form. This dark age ended when the first stars and galaxies began emitting ultraviolet light, ionizing the surrounding hydrogen and making the universe transparent to light. The CIB contains imprints of this reionization era, providing a unique way to study how and when it occurred. Moreover, the CIB serves as a crucial link in multi-wavelength astronomy, which combines observations across the electromagnetic spectrum, from radio waves to gamma rays, to build a complete picture of cosmic phenomena. For instance, by comparing the CIB with the cosmic microwave background (CMB), scientists can study how galaxies formed and evolved within the large-scale structure of the universe. Similarly, correlating the CIB with X-ray observations helps identify regions where black hole activity and star formation were particularly intense. As the technology for observing the cosmos improves, the CIB's potential to reveal new insights grows exponentially. Instruments like the James Webb Space Telescope, JWST, are already revolutionizing our understanding of the infrared universe. JWST's ability to capture high-resolution images and spectra of distant galaxies allows researchers to directly compare these observations with the diffuse light of the CIB, linking individual objects to the larger cosmic background. This synergy between targeted observations and broad surveys is helping to unlock the secrets hidden in the CIB. Looking further ahead, upcoming missions like the Nancy Grace Roman Space Telescope and the next generation of ground-based observatories will push the boundaries even further. These instruments will be equipped with cutting-edge detectors and data analysis tools, enabling them to probe the faintest and most distant sources of the CIB. Combined with advances in computational astrophysics, these observations promise to bring us closer to a comprehensive understanding of the universe's history. The cosmic infrared background is not just a scientific puzzle, it's also a reminder of the profound interconnectedness of the universe. The faint light we study today carries the stories of countless stars and galaxies, each a chapter in the epic tale of cosmic evolution. As we delve deeper into the mysteries of the CIB, we are not only uncovering the secrets of the universe's past but also laying the groundwork for future discoveries. The journey may be complex, but the rewards, both in terms of knowledge and the sheer wonder of understanding our place in the cosmos, are immeasurable. The exploration of the cosmic infrared background (CIB) is an ongoing narrative, one that reflects the intricate dance of light and matter across billions of years. This faint glow, a relic of the earliest days of star formation, acts as a cosmic archive that preserves the story of the universe's infancy. However, it also teases us with questions that are as profound as the answers it provides. One of the most intriguing aspects of the CIB is its connection to hidden galaxies. Many galaxies in the early universe were shrouded in thick clouds of gas and dust, making them invisible to optical telescopes. Yet, these same galaxies emitted copious amounts of infrared light as the dust absorbed starlight and re-radiated it at longer wavelengths. The CIB, therefore, acts as a beacon, highlighting regions of intense star formation that would otherwise go unnoticed. By studying these signals, scientists are uncovering a population of galaxies that are essential to understanding the universe's evolution, but remain invisible in other parts of the spectrum. This brings us to the challenge of separating foreground emissions from the CIB itself. The infrared sky is cluttered with signals from a variety of sources, including stars, interstellar dust, and even our own galaxy, the Milky Way. Isolating the CIB requires advanced techniques in image processing and data analysis. For instance, researchers often use statistical methods to subtract the contributions of nearby stars and galaxies, revealing the underlying diffuse light. These methods are constantly evolving, driven by the need to make sense of increasingly complex datasets. The potential to detect faint signals from the earliest epochs of galaxy formation also makes the CIB an invaluable tool for testing theoretical models. For example, cosmologists use simulations to predict how the first galaxies formed and evolved under the influence of gravity, dark matter, and cosmic expansion. By comparing these simulations with the observed properties of the CIB, scientists can refine their models, improving our understanding of the universe's early stages. But the CIB is not just about looking back in time, it also has implications for the future. One fascinating application lies in the study of cosmic feedback mechanisms, the processes by which stars and galaxies influence their surroundings. For instance, massive stars and supernovae can inject energy into their environments, shaping the formation of new stars and galaxies. By analyzing the CIB, astronomers can trace the impact of these feedback processes across cosmic history, shedding light on how galaxies evolve over billions of years. Another cutting-edge area of research involves the interplay between the CIB and gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant galaxies passes near massive objects, such as galaxy clusters, it bends and magnifies, creating a lensing effect. The CIB is an ideal probe for studying this effect because its diffuse nature makes it sensitive to the large-scale distribution of matter in the universe. By mapping the CIB in regions where lensing occurs, scientists can gain insights into the structure and distribution of dark matter, which constitutes most of the universe's mass. The CIB is also a crucial piece of the puzzle in the search for primordial black holes, a hypothetical type of black hole that could have formed in the early universe. These black holes are thought to emit radiation as they interact with surrounding matter, and their signatures might be detectable in the infrared background. If confirmed, the existence of primordial black holes could have profound implications for our understanding of dark matter and the origins of the universe. As we continue to explore the CIB, we are reminded of the interconnectedness of all cosmic phenomena. The faint light we detect is not merely a relic of the past but a living record of the processes that continue to shape the universe. Each new discovery adds a layer of complexity to our understanding, making the study of the CIB one of the most dynamic and exciting fields in modern astronomy. The next steps in CIB research will likely involve even more sophisticated technologies and collaborations. International projects like the Euclid mission and the Square Kilometre Array (SKA) are expected to provide unprecedented data on the distribution of galaxies and the structure of the cosmic web. These efforts will complement studies of the CIB, creating a comprehensive picture of the universe's evolution from the Big Bang to the present day. At its core, the cosmic infrared background is a reminder of the universe's vastness and the intricate interplay of forces that govern its behavior. It challenges us to think beyond the visible, to explore the unseen, and to embrace the mysteries that define our existence. With each new discovery, we inch closer to unraveling the secrets of the cosmos, guided by the faint glow of light that has traveled billions of years to reach us. And yet, the more we learn, the more questions arise. What lies beyond the horizons of our current understanding? How do the phenomena captured in the CIB connect to the broader tapestry of the universe? These questions drive the relentless pursuit of knowledge, ensuring that the study of the cosmic infrared background will remain a cornerstone of astronomy for generations to come. The journey of understanding the cosmic infrared background (CIB) is far from complete. As we continue to probe the universe, new discoveries are likely to arise that challenge our current understanding and open up fresh avenues of exploration. Each piece of data we collect from the CIB, every subtle fluctuation in its intensity, every shift in its spectrum, adds to a broader, more intricate picture of the universe's development. It's as if we are slowly assembling a vast, cosmic jigsaw puzzle, and with each new piece, the overall image becomes clearer, yet more complex and detailed. One of the most compelling aspects of CIB research lies in its potential to reveal insights about early galaxy evolution. Galaxies, those massive collections of stars, gas, and dust, didn't suddenly appear fully formed after the Big Bang. They evolved over billions of years, growing and merging with each other, changing their shape and structure. Understanding the detailed history of these galaxies, particularly those that existed in the very early universe, is essential to grasping the fundamental processes that led to the formation of the universe as we see it today. The CIB plays a crucial role in this quest by allowing astronomers to study the birth of galaxies in a way that's impossible using visible light alone. While optical telescopes provide us with stunning views of mature galaxies in the modern universe, they struggle to peer back far enough in time to observe the universe's infancy. The CIB, however, provides a unique window into the early stages of galaxy formation. By detecting the infrared light emitted by ancient galaxies, light that has been stretched and redshifted over billions of years, we can gain insights into how galaxies first took shape. This is particularly important because early galaxies were often very different from the ones we observe today. They were smaller, more irregular in shape, and lacked the abundant metals that make up modern galaxies. Studying the CIB allows scientists to understand the composition of these early galaxies, helping us trace how they developed and how they eventually contributed to the larger-scale structures in the universe, such as galaxy clusters and superclusters. But the study of the CIB is not just about understanding the evolution of galaxies. It also provides valuable information about the formation of the first supermassive black holes. These black holes, which reside at the centers of most galaxies, are thought to have formed very early in the universe's history, possibly within the first few 100 million years after the Big Bang. The relationship between supermassive black holes and their host galaxies is still one of the greatest mysteries in modern astronomy. Did these black holes form first, pulling in surrounding matter and creating galaxies around them? Or did galaxies form first, with supermassive black holes developing later? The CIB can provide some answers to these questions. As light from early galaxies passes through regions near supermassive black holes, it can be affected by the intense gravitational fields and high-energy radiation emitted by these objects. Studying the CIB allows scientists to detect these influences and trace the development of both galaxies and supermassive black holes in tandem. Furthermore, the interaction between galaxies and their environment is another area where the CIB plays a significant role. In the early universe, galaxies were not isolated but rather interacted with one another, and with the gas and dust that filled the space between them. These interactions could trigger bursts of star formation or lead to the formation of new structures like galaxy clusters. The CIB acts as a kind of cosmic map, highlighting regions where these interactions occurred and allowing scientists to trace the flow of matter and energy across vast cosmic distances. What's particularly exciting is that these early stages of galaxy evolution might hold clues to the formation of the first stars, known as population 3 stars. These stars, composed almost entirely of hydrogen and helium, are believed to have formed shortly after the Big Bang, before the universe was enriched with heavier elements like carbon and oxygen. These stars were far more massive than those that exist today, and their death in supernova explosions likely played a crucial role in seeding the universe with the heavier elements necessary for life as we know it. However, finding evidence of these stars is extraordinarily difficult, as they have long since faded away. The CIB offers a potential way to detect their presence. The infrared light emitted by these stars, redshifted across vast distances, might still linger in the background radiation we observe today. By carefully studying the CIB, scientists hope to uncover traces of these long-lost stars and better understand the processes that led to the formation of the elements that make up the universe. The quest to understand the CIB also opens the door to new physics. As we study the faint light from the early universe, we begin to encounter phenomena that challenge our current understanding of cosmology. For instance, dark energy, the mysterious force driving the accelerated expansion of the universe, might leave subtle imprints on the CIB. Understanding these imprints could help us refine our models of cosmic expansion and give us deeper insight into the nature of dark energy itself. Similarly, dark matter, which makes up a significant portion of the universe's mass, could influence the CIB in ways that are still not fully understood. Dark matter doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes. However, it interacts gravitationally with visible matter, and its effects can be seen in the distribution of galaxies and the cosmic web. By studying the CIB in conjunction with other cosmic surveys, scientists may be able to map the distribution of dark matter in the universe and better understand its role in shaping the cosmos. The more we explore the CIB, the more we realize that it is not just a tool for looking backward but also a key to understanding the future of the universe. By studying the light left over from the early days of star formation, we are not only tracing the history of the universe but also gaining insights into its future trajectory. What will the universe look like billions of years from now? How will galaxies continue to evolve? Will star formations slow down even further, or will new processes emerge that shape the cosmic landscape in ways we can't yet predict? These are questions that lie at the heart of ongoing cosmological research, and the CIB is one of the most valuable clues in our search for answers. It offers us a glimpse into the past while simultaneously helping us make predictions about the universe's future. As technology advances, and our ability to study the cosmos improves, the CIB will continue to play a pivotal role in reshaping our understanding of the universe. In the coming years, we can expect even more breakthroughs as new telescopes, observatories, and space missions come online. The combination of these technological advancements with the wealth of data already gathered will push our understanding of the CIB and its implications for cosmology to new heights. These discoveries will not only shed light on the mysteries of the early universe but also deepen our appreciation for the vast and interconnected cosmos that we are a part of. The study of the cosmic infrared background is an exciting, ever-evolving field that has the potential to transform our understanding of the universe. It is a reminder of how much we still have to learn, how much remains hidden in the depths of space, and how the light of distant stars continues to guide us on our journey of discovery. As we continue to explore the cosmic infrared background (CIB), it's important to consider the scientific techniques and technologies that are making these discoveries possible. One of the most significant developments in recent years is the advancement of space-based observatories. Unlike ground-based telescopes, which are limited by the Earth's atmosphere, space telescopes like the James Webb Space Telescope (JWST) provide an unobstructed view of the infrared universe. JWST, in particular, has the ability to detect faint infrared signals from the earliest galaxies, making it a critical tool in studying the CIB. In fact, JWST is already revolutionizing our understanding of the early universe. Its advanced infrared capabilities allow it to observe the faintest, most distant objects, many of which are so far away that their light has been stretched and redshifted into the infrared part of the spectrum. By studying this redshifted light, scientists can infer a wealth of information about the conditions of the universe when these objects were first forming. Another key factor that makes these observations possible is the technique of gravitational lensing. Gravitational lensing occurs when a massive object, such as a galaxy or a galaxy cluster, bends the path of light from objects behind it. This phenomenon can magnify and distort the light from distant objects, allowing astronomers to study galaxies that would otherwise be too faint to detect. In some cases, gravitational lensing provides a natural, cosmic magnifying glass that brings the earliest galaxies into clearer view, allowing scientists to study their structure, composition, and star formation rates. By combining gravitational lensing with infrared observations from space-based telescopes, researchers can unlock secrets about the earliest epochs of galaxy formation. These discoveries are not only revealing how galaxies and stars form but are also shedding light on the evolution of the universe's most fundamental properties. For example, by studying the distribution of galaxies through the CIB, astronomers can learn more about the universe's overall geometry, how matter and energy are distributed on the largest scales, and how these distributions have changed over time. The importance of the CIB is further highlighted when we consider how it can contribute to answering some of the most profound questions in cosmology. One such question is related to the nature of dark energy, the mysterious force that is causing the universe to accelerate in its expansion. While dark energy has been inferred from observations of distant supernovae and the cosmic microwave background (CMB), its exact properties remain elusive. Some scientists believe that the CIB may contain subtle clues about dark energy, particularly in how the expansion of the universe affects the light emitted by distant galaxies. For example, if dark energy is influencing the rate of cosmic expansion, it could alter the way the CIB is distributed or change the light that we observe from the early universe. By studying these variations, cosmologists could gain new insights into the true nature of dark energy, one of the biggest mysteries in modern science. At the same time, dark matter, which makes up roughly 27% of the universe's total mass, is also intertwined with the study of the CIB. Dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, its presence is inferred from its gravitational effects on visible matter, and it plays a crucial role in the formation of galaxies and large-scale structures in the universe. By studying the CIB in conjunction with other forms of cosmic radiation, researchers hope to map the distribution of dark matter and learn more about its properties. The subtle effects of dark matter could be detected in the CIB's light, offering a way to probe its nature and behavior more directly. The complexity of the universe and the interconnectedness of its many mysteries make studying the CIB an incredibly exciting and rewarding pursuit. Every discovery, every new piece of information, brings us closer to understanding not just the history of the universe, but also its future trajectory. The CIB represents the faint glow of stars long gone, but it also carries with it the story of the universe's most formative years, the moments when the first galaxies and stars began to take shape. As technology advances, the possibilities for studying the CIB will only grow. In the next few decades, new missions and observatories are expected to provide even more precise measurements and deeper insights into the early universe. These innovations may allow us to look back even further in time, perhaps even to the era before the first stars were born, providing a glimpse into the very beginning of the cosmos itself. The study of the cosmic infrared background is more than just an academic pursuit. It is a journey into the very heart of the universe. It is a way to explore our origins, to understand the forces that shape the galaxies, stars, and planets that make up our cosmic neighborhood. The faint infrared light that has traveled through space for billions of years carries with it the secrets of the universe's earliest days, and every step forward in understanding the CIB brings us closer to unlocking those secrets. In the coming years, as our tools and techniques continue to improve, we will likely find ourselves facing even more profound questions about the nature of the cosmos. How did the first galaxies form and evolve? What role did dark energy and dark matter play in shaping the universe's large-scale structure? What mysteries remain hidden in the faint glow of the cosmic infrared background? As we continue to push the boundaries of knowledge, one thing is certain: the study of the CIB will be at the forefront of our efforts to uncover the most fundamental truths about the universe. The cosmic infrared background serves as a window into the distant past, and through it, we can begin to understand the vast and intricate history of the universe. It's a story that spans billions of years, a story of stars being born, galaxies merging, and the universe expanding at an unimaginable rate. By continuing to study the CIB, we are not just looking at the remnants of ancient star-forming regions. We are peering into the very essence of the universe itself, and with every discovery, we inch closer to understanding the cosmos and our place within it. As we continue exploring the cosmic infrared background (CIB), we delve deeper into understanding not only the earliest galaxies but also the mysterious processes that shape the universe. The light we observe in the CIB is often referred to as the afterglow of the universe's formation, a remnant from the time when the first stars and galaxies began to form. It offers a tantalizing glimpse into the early phases of the universe's evolution, helping us connect the dots between theoretical models and real, observable phenomena. One of the most exciting aspects of the CIB is its potential to provide insight into the Reionization epoch. Reionization is a phase in the universe's history, occurring roughly 1 billion years after the Big Bang, when the universe transitioned from being opaque to transparent. During this time, the universe's neutral hydrogen gas was ionized by the first stars and galaxies, allowing light to travel freely through space. The CIB contains residual light from this process, and studying its characteristics can help us understand the nature and timing of reionization. Reionization marks a pivotal moment in the history of the cosmos. Before reionization, the universe was a dark and foggy place, with light being absorbed and scattered by the dense clouds of hydrogen gas. As the first stars formed and began emitting ultraviolet radiation, they ionized the surrounding hydrogen gas, creating bubbles of ionized hydrogen. This process gradually cleared the fog of the early universe, allowing light to travel freely across vast distances. The faint infrared glow we observe today is a direct consequence of this dramatic transformation. But despite its significance, much about reionization remains shrouded in mystery. Scientists are still debating exactly when it occurred, how it unfolded, and what role different types of galaxies and stars played in the process. Some models suggest that reionization was a gradual process, occurring over hundreds of millions of years, while others propose that it may have happened in a more sudden, dramatic fashion. By studying the CIB, we can gain clues about the precise timing and mechanisms of reionization, providing us with a better understanding of the early universe's evolution. Additionally, the spatial distribution of the CIB offers important information about the structure of the early universe. The CIB is not uniform across the sky. Instead, it contains fluctuations that correspond to the distribution of galaxies in the distant past. By studying these fluctuations, astronomers can map the large-scale structure of the universe as it was when it was still in its infancy. These maps can reveal the locations of the first galaxies, the density of matter in different regions of the universe, and the ways in which galaxies clustered together in the early cosmos. This kind of information is crucial for testing cosmological models, particularly those related to the growth of structure in the universe. According to the current model of cosmology, the universe began as a nearly uniform and smooth state, with tiny fluctuations in the density of matter. Over time, gravity caused these fluctuations to grow, eventually leading to the formation of galaxies and clusters of galaxies. The study of the CIB provides a unique opportunity to observe the effects of this process in action, offering clues about how galaxies first began to assemble, and how they evolved over time. Furthermore, the CIB's relationship with the cosmic microwave background (CMB) cannot be overstated. The CMB is the oldest light we can observe, dating back to just 380,000 years after the Big Bang. It provides a snapshot of the universe in its infancy, when it was still in a hot, dense state. In contrast, the CIB is the residual light from the later stages of galaxy formation, and it provides a view of the universe when it had cooled sufficiently for stars and galaxies to form. Together, the CMB and CIB form a powerful combination of data, helping us piece together the entire story of the universe's evolution, from the Big Bang to the present day. The CMB and CIB offer complementary views of the universe's past. While the CMB captures the universe's earliest moments, the CIB sheds light on the subsequent development of galaxies and large-scale structures. This complementary relationship allows scientists to test and refine their models of cosmological evolution, as they compare predictions with observations from both the CMB and CIB. As we look to the future, there are many exciting developments on the horizon that will further advance our understanding of the CIB. In particular, the next generation of space telescopes promises to push the boundaries of infrared astronomy even further. The James Webb Space Telescope has already made significant strides, but even more advanced instruments, such as the Nancy Grace Roman Space Telescope, will be able to capture even fainter signals from the early universe, providing us with a clearer picture of galaxy formation, reionization, and the growth of cosmic structures. Additionally, the development of new ground-based observatories equipped with powerful infrared detectors will complement space-based efforts. These observatories, located in high-altitude regions far from light pollution, are capable of detecting faint infrared light and studying the CIB in unprecedented detail. By combining data from both ground-based and space-based telescopes, astronomers will be able to create a more complete and accurate picture of the universe's early history. Another promising avenue for exploration is the potential for multi-wavelength astronomy, which involves combining data from different regions of the electromagnetic spectrum. While infrared observations are key to studying the CIB, other wavelengths of light, such as X-rays and radio waves, also provide valuable information about the universe's early stages. By analyzing data across multiple wavelengths, scientists can gain a more holistic understanding of the processes that shape the universe, from the formation of the first stars to the emergence of galaxies. The cosmic infrared background remains one of the most exciting and mysterious aspects of modern cosmology. It serves as a window into the distant past, allowing us to observe the faint glow of the first galaxies and uncover the secrets of the early universe. By continuing to study the CIB, we can gain insights into the formation and evolution of galaxies, the processes of reionization and star formation, and the fundamental nature of dark matter and dark energy. Each new discovery brings us one step closer to understanding the universe's origins and the forces that have shaped it. As technology advances and our observational capabilities continue to improve, the future of CIB research looks bright. New missions, improved telescopes, and advanced computational models will enable us to explore the earliest epochs of the universe in greater detail than ever before. The mysteries of the cosmic infrared background are far from being fully unraveled, and with each new piece of the puzzle, we move closer to unlocking the most profound questions of cosmology. The universe, it seems, is full of secrets waiting to be discovered, and the CIB is one of the most exciting clues in this grand cosmic mystery. The future of studying the cosmic infrared background (CIB) looks increasingly promising, with emerging technologies and ongoing research set to push the boundaries of what we know about the early universe. As astronomers continue to analyze the faint infrared light that has traveled across vast stretches of space and time, there are still many unanswered questions that the CIB may hold the key to solving. The CIB is not just a passive remnant of the past, but a living record, rich with information about the formation of the first galaxies, the nature of dark matter and dark energy, and even the elusive details of the cosmic history that we have yet to fully understand. One of the key challenges scientists face when studying the CIB is its faintness. The light that makes up the CIB has traveled for billions of years, often passing through dense clouds of gas and dust, which can scatter and absorb it. This makes the CIB a tricky target to observe. However, with advancements in infrared technology, including more sensitive detectors and better space telescopes, scientists are able to collect more detailed data. Instruments like the James Webb Space Telescope, JWST, and the Spitzer Space Telescope have already made tremendous contributions by observing the infrared sky in unprecedented detail, but the potential for future discoveries remains vast. The CIB itself is not just a single signal, but a complex mix of emissions from a variety of sources. The primary contributors to the CIB are the first generations of stars, as well as galaxies in the early stages of formation. As these stars and galaxies emit light, much of it is absorbed and re-emitted by dust and gas in the intergalactic medium. This process causes the light to shift to longer wavelengths, making it detectable as infrared radiation. While this infrared light gives us crucial information about the formation and evolution of the universe, it also provides hints about the nature of the material that filled the early universe, material that we still do not fully understand. For example, the study of the CIB could provide further insight into the enigmatic role of dark matter and dark energy in shaping the cosmos. Dark matter, a form of matter that doesn't emit light but exerts gravitational influence on visible matter, is thought to have played a crucial role in the formation of the first galaxies. Understanding how dark matter interacted with the light from early stars and galaxies can help us refine our models of galaxy formation and evolution. Similarly, dark energy, which is believed to be responsible for the accelerated expansion of the universe, might also leave imprints in the CIB that could help us understand its nature. In addition to its role in tracing the formation of galaxies, the CIB is also important for understanding the process of galactic evolution. The galaxies that we observe today have undergone billions of years of development, with many having experienced phases of intense star formation, mergers, and interactions. The infrared light from these early galaxies is a valuable tool for understanding how they grew from small, fragmented regions of gas and dust into the massive, complex systems that we see today. The study of the CIB allows astronomers to observe these galaxies at a much earlier stage in their development, providing insights into the processes that led to their growth and transformation over time. Another fascinating aspect of the CIB is its connection to the formation of the first black holes. These supermassive objects, which are found at the centers of most galaxies, are believed to have formed in the early universe, perhaps even before the first galaxies themselves. The light we detect in the CIB may offer clues about the formation and growth of these black holes, particularly the mechanisms by which they acquired their enormous masses. Understanding the relationship between black holes and their host galaxies is a crucial piece of the puzzle when it comes to understanding the overall evolution of the universe. The CIB also offers tantalizing clues about the early chemical composition of the universe. As the first stars formed and began to burn, they synthesized elements like hydrogen, helium, and heavier elements like carbon, oxygen, and iron. These elements were later dispersed into space during supernova explosions, contributing to the chemical richness of galaxies. The infrared light from these early stars and galaxies can tell us about the types of elements that were present in the first galaxies and how they contributed to the chemical evolution of the universe. Moreover, the distribution of the CIB across the sky can reveal information about the large-scale structure of the universe. Just as the cosmic microwave background (CMB) provides a snapshot of the universe's state shortly after the Big Bang, the CIB allows us to study the universe at a later stage, when galaxies had begun to form. By mapping the CIB and analyzing its fluctuations, scientists can create detailed maps of the universe's large-scale structure and study the ways in which matter has clustered together over time. This information is essential for testing theories of cosmic inflation and the formation of galaxies. In the coming decades, astronomers will have access to even more advanced tools for studying the CIB. For example, future space observatories like the Nancy Grace Roman Space Telescope and the Euclid mission are expected to improve our understanding of the cosmic infrared background by providing more detailed and accurate measurements of its properties. These telescopes will help to refine our knowledge of the early universe, offering new insights into the processes that shape the cosmos and the formation of galaxies, stars, and black holes. Ground-based telescopes are also making significant contributions to the study of the CIB. For example, the Atacama Large Millimeter/Submillimeter Array, ALMA, located in the Chilean desert, is one of the most powerful radio observatories in the world. ALMA is capable of observing the universe in the millimeter and submillimeter wavelengths, which overlap with the infrared spectrum and provide complementary data to what is being observed from space. By combining data from both ground-based and space-based telescopes, scientists can achieve a more comprehensive understanding of the universe's earliest stages. As we continue to explore the cosmic infrared background, one of the most exciting aspects is the potential for new discoveries. The universe is vast and filled with mysteries, and the study of the CIB offers an unprecedented opportunity to unlock some of its deepest secrets. Each new piece of information we gain about the CIB helps to fill in the gaps of our understanding of the cosmos, shedding light on the forces and processes that have shaped the universe over billions of years. The CIB is not just a faint remnant of the past, but a dynamic and evolving window into the universe's history. By studying it, we gain a deeper understanding of the origins of galaxies, the nature of dark matter and dark energy, the formation of black holes, and the chemical composition of the universe. As our observational tools continue to improve and our theoretical models evolve, the cosmic infrared background will undoubtedly continue to be a key focus of research, offering new insights into the mysteries of the universe. As we look toward the future, it's important to recognize that the study of the cosmic infrared background (CIB) holds potential not only for answering long-standing questions but also for posing entirely new ones. The further we peer into the distant reaches of space, the more we uncover about the early universe and its subsequent evolution. By expanding our understanding of the CIB, scientists may one day be able to answer some of the most profound questions in cosmology, questions that touch on the very fabric of the universe itself. One of the most compelling areas of investigation related to the CIB is the study of cosmic reionization. This period, which occurred roughly 1 billion years after the Big Bang, marks a dramatic transformation in the universe. During this time, the first stars and galaxies began to form, emitting vast amounts of ultraviolet radiation that reionized the neutral hydrogen gas that filled the early universe. This process set the stage for the formation of the structures we see today: galaxies, stars, and the vast cosmic web of matter. The CIB plays a crucial role in tracing the aftereffects of this period of reionization, helping astronomers understand the timeline and processes involved. The light that we detect today from the CIB may represent the last vestiges of this critical phase in cosmic history. However, studying cosmic reionization through the CIB is far from straightforward. The process was likely complex and took place over a prolonged period of time, with multiple sources of radiation contributing to the ionization of the hydrogen gas. Understanding the detailed processes that occurred during this period requires careful analysis of the CIB's spectral signature, as well as the development of sophisticated models that can account for the various contributions to the background light. By analyzing how the CIB changes at different wavelengths, scientists hope to build a more complete picture of the reionization process and its impact on the evolution of the universe. Another exciting avenue of research is the study of galactic mergers and interactions. Galaxies, like living organisms, evolve over time through a variety of processes, including mergers, accretion, and the exchange of gas and dust. These interactions often trigger bursts of star formation, and the resulting infrared radiation from these processes contributes to the CIB. By studying the infrared light emitted by galaxies during these interactions, astronomers can gain insight into how galaxies evolve and how their various components, stars, gas, and dust, interact over time. Recent discoveries have revealed that some of the most massive galaxies in the universe are the result of mergers between smaller galaxies. These events are believed to play a crucial role in shaping the structure of galaxies, as well as in the formation of supermassive black holes at their centers. The infrared light from these merging galaxies, often obscured by thick clouds of dust, can be seen as a faint signal in the CIB. By carefully analyzing the distribution of this light, scientists are able to reconstruct the history of galaxy mergers and their role in the formation of the large-scale structures that we observe in the universe today. In addition to these more well-established areas of research, the study of the CIB may also have implications for some of the more speculative aspects of cosmology. For example, the nature of dark matter remains one of the greatest mysteries in modern astrophysics. While its existence is inferred from its gravitational effects on visible matter, we still know very little about what dark matter actually is. Some theories suggest that dark matter could consist of exotic particles, such as WIMPs, weakly interacting massive particles, or axions, which do not interact with electromagnetic radiation. However, dark matter may also have a subtle effect on the infrared light detected in the CIB. If dark matter is present in the early universe, it could have interacted with the gas and dust that made up the first galaxies, affecting the way that light was emitted and absorbed. Likewise, dark energy, which is thought to be responsible for the accelerated expansion of the universe, could leave traces in the cosmic infrared background. Dark energy is still poorly understood, but its impact on the expansion of space is undeniable. As we continue to improve our understanding of the CIB, we may uncover new insights into how dark energy has influenced the evolution of the universe, and how its effects can be observed through the faint infrared radiation left behind by the first stars and galaxies. Perhaps one of the most intriguing aspects of the CIB is its potential to help us understand the early chemical composition of the universe. The study of the CIB can provide valuable information about the types of elements that were present in the first galaxies and how these elements were synthesized in the cores of stars. The formation of heavier elements, such as carbon, oxygen, and iron, is thought to occur in the interiors of stars through nuclear fusion. These elements are then dispersed into space during supernova explosions, enriching the interstellar medium and contributing to the formation of new generations of stars and planets. By studying the infrared light from early galaxies, scientists can trace the evolution of these elements over cosmic time, providing a deeper understanding of the chemical history of the universe. Moreover, the cosmic infrared background may help us unravel the mysteries of cosmic inflation. Inflation is the theory that the universe underwent a rapid, exponential expansion in the first few moments after the Big Bang. This expansion would have stretched the fabric of space-time and created the conditions for the formation of galaxies, stars, and other cosmic structures. While much about inflation remains speculative, the CIB offers a unique window into the aftermath of this period of rapid expansion. By examining the subtle fluctuations in the CIB, scientists may be able to detect imprints of inflationary processes and gain new insights into the very early moments of the universe. While the study of the CIB is still in its early stages, it has already yielded remarkable discoveries that have transformed our understanding of the universe. The faint infrared light that permeates space holds a wealth of information about the early history of the cosmos, from the formation of galaxies and stars to the nature of dark matter, dark energy, and the fundamental forces that shape the universe. As our technological capabilities continue to improve and our models of the universe become more sophisticated, the study of the CIB will undoubtedly remain one of the most exciting and promising frontiers in modern cosmology. In the coming decades, the combination of ground-based and space-based telescopes will continue to provide new and increasingly detailed observations of the CIB. Instruments like the James Webb Space Telescope, which is capable of observing the universe in the infrared part of the spectrum, will revolutionize our ability to study the early universe. By observing the faint infrared light emitted by the first galaxies, the CIB will provide astronomers with a clearer picture of how the universe evolved from the hot, dense state of the Big Bang to the complex and structured cosmos we observe today. As we continue to unlock the secrets hidden within the cosmic infrared background, we move one step closer to understanding the true nature of the universe, its origins, its evolution, and the forces that continue to shape its future. The study of the CIB is a crucial part of this journey, offering a glimpse into the early stages of cosmic history and the key to unraveling some of the universe's most profound mysteries. As we venture deeper into the study of the cosmic infrared background (CIB), one of the most intriguing aspects to explore is its potential for revealing the distribution of matter across vast distances. The CIB is not just a background glow, it can tell us about the structures that populate the universe, including galaxies, gas clouds, and even the dark matter that is not directly observable by traditional means. These insights are crucial for understanding how galaxies form, evolve, and interact within the cosmic landscape. The challenge here is that much of the CIB comes from ancient star-forming regions that existed billions of years ago. These regions were often obscured by thick clouds of dust, which absorbed ultraviolet light from young stars and re-emitted it as infrared radiation. As a result, we are looking at a sort of cosmic afterglow, a record of events that took place long before our own time. This ancient light provides us with a snapshot of what the universe looked like at its very earliest stages, offering valuable clues about how the first galaxies and stars formed. To study this ancient glow, scientists have relied on a range of advanced infrared observatories and space telescopes. Instruments like the Spitzer Space Telescope, which operated from 2003 to 2020, were able to detect infrared radiation from distant galaxies and help map the early universe. The Herschel Space Observatory, launched by the European Space Agency, also made significant contributions by detecting far-infrared light from galaxies that were previously too faint to be seen in visible light. These observations have led to major discoveries about the structure of the early universe, including the clustering of galaxies and the role of dust and gas in the formation of new stars. Yet, as promising as these telescopes were, the James Webb Space Telescope, JWST, launched in December 2021, represents the next frontier in the study of the CIB. Webb's advanced infrared capabilities allow it to peer even further back in time, capturing light that has traveled for billions of years. The telescope is designed to study the universe in the infrared spectrum, allowing astronomers to observe regions of space that were previously hidden from view. JWST's ability to observe faint galaxies and star-forming regions is already providing invaluable data, shedding light on the universe's early history and offering clues about the role of the CIB in shaping the cosmos. One of the key features of JWST is its ability to detect the faintest infrared signals, including those emitted by objects that formed when the universe was only a few 100 million years old. These early galaxies were much smaller and less luminous than the massive galaxies we see today, but they played a critical role in shaping the universe's evolution. The light they emitted was absorbed by the surrounding gas and dust, and over time, it combined to create the cosmic infrared background we observe today. By studying the CIB with JWST, astronomers hope to learn more about the process of galaxy formation and the conditions that allowed these early galaxies to emerge from the primordial soup of the early universe. One of the most exciting prospects for JWST is its ability to detect the first stars. These stars, known as population 3 stars, were the first generation of stars to form after the Big Bang. They were made primarily of hydrogen and helium, the two lightest elements created during the Big Bang, and they had no heavy elements like carbon or oxygen. Population 3 stars were massive and short-lived, burning out in supernova explosions that created the heavy elements necessary for the formation of planets, life, and everything else we observe in the universe today. By studying the CIB, we can indirectly observe the aftereffects of these first stars, allowing us to probe the conditions of the early universe when these stars began to shine. As we continue to investigate the CIB, it is essential to recognize that new discoveries are still being made. While we have learned a great deal about the early universe, there are still many questions that remain unanswered. For example, the precise role of black holes in shaping the CIB is still not fully understood. Supermassive black holes, which reside at the centers of most galaxies, are known to play a key role in the evolution of galaxies. They can drive powerful outflows of gas and energy, influencing the surrounding environment. However, the way these black holes interact with the cosmic infrared background is still a topic of active research. In addition, there is the question of the origins of cosmic dust. While we know that dust plays a crucial role in shaping the CIB by absorbing ultraviolet light and re-emitting it as infrared radiation, the exact origins of this dust remain elusive. Some of the dust may have formed in the winds of dying stars, while other dust grains could have been produced in the violent explosions of supernovae. Understanding the formation of dust in the early universe is essential for understanding the overall structure of galaxies and the processes that lead to star formation. Another unresolved mystery is the evolution of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. They are typically located in regions where the matter density is high, and they are thought to have formed early in the history of the universe. The light emitted by galaxies in these clusters contributes to the CIB, but the precise way in which galaxy clusters evolve over time remains unclear. By studying the CIB in the context of galaxy clusters, scientists can learn more about how these massive structures formed and how they continue to evolve. Despite these unresolved questions, the study of the cosmic infrared background has already led to some remarkable breakthroughs in our understanding of the universe. For example, astronomers have discovered that the early universe was much more energetic than previously thought. The CIB suggests that the first galaxies and stars were much more active than we had anticipated, and this has important implications for our understanding of cosmic evolution. It also suggests that the universe underwent a rapid period of star formation in its early years, challenging previous assumptions about the pace at which galaxies formed. Furthermore, the CIB is helping to refine our understanding of the large-scale structure of the universe. By studying the distribution of galaxies, gas, and dark matter in the CIB, scientists are piecing together the intricate web of cosmic filaments that stretches across the universe. This web, known as the cosmic web, is made up of vast stretches of dark matter and gas that connect galaxies and galaxy clusters. Understanding how the CIB relates to the cosmic web can help us better understand the forces that have shaped the large-scale structure of the universe and how it continues to evolve. The discovery of the CIB itself is a testament to the power of astronomical exploration. For decades, the faint glow of infrared radiation from distant galaxies remained undetected, hidden beneath the brighter signals from nearby stars and galaxies. But with the development of new instruments and technologies, we have been able to peer deeper into space and uncover this hidden aspect of the universe. The study of the CIB has transformed our understanding of the early universe, and it continues to provide valuable insights into the processes that shape the cosmos. Looking ahead, the study of the CIB is poised to make even greater contributions to our understanding of the universe. As technology continues to advance and new observatories are launched, we can expect even more detailed observations of the cosmic infrared background. These advancements will help to answer many of the lingering questions about the early universe, including the formation of galaxies, the role of dark matter and dark energy, and the conditions that allowed life to emerge. The cosmic infrared background is not just a faint glow that fills the universe. It is a window into the very early history of the cosmos. It offers a unique opportunity to study the formation and evolution of galaxies, the role of dark matter, and the conditions that led to the birth of stars and galaxies. As we continue to explore this fascinating aspect of the universe, we can expect to uncover new and exciting discoveries that will reshape our understanding of the cosmos. With the ongoing advancement of technology and the continued efforts of astronomers, the study of the CIB will undoubtedly remain one of the most exciting frontiers in the field of cosmology for years to come. As we continue to explore the cosmic infrared background (CIB), one of the most compelling aspects to consider is the relationship between the CIB and cosmic evolution. The study of the background radiation is not just an exploration of the past. It is integral to understanding how the universe has evolved over billions of years. By studying the faint infrared glow emitted by ancient galaxies and star-forming regions, we can begin to piece together a story of how the universe transformed from a primordial soup of gas and dust into the structured cosmos we see today. A key concept here is the evolution of galaxies. Galaxies are the fundamental building blocks of the universe, and their formation and development are intricately tied to the CIB. In the early universe, galaxies were much smaller and less structured than they are today. They were often composed of young stars, gas clouds, and dust, materials that played a significant role in shaping the cosmic infrared background. These galaxies were undergoing intense star formation, a process that produced copious amounts of energy. This energy would be absorbed by dust and gas in the galaxy, only to be re-emitted in the form of infrared radiation. The resulting glow from these young galaxies has become a key signature of the cosmic infrared background. As we study the CIB, we are not only looking at ancient star-forming galaxies but also at the complex processes that led to the formation of larger galaxies. The universe's early galaxies, often referred to as protogalaxies, were small, irregularly shaped objects that eventually merged to form the larger galaxies we see today. These mergers played a pivotal role in galaxy evolution, helping to build the massive structures that populate the universe. By observing the CIB, we can study the ways in which these early galaxies interacted and how they eventually coalesced into the large, organized structures that make up the modern universe. One of the central challenges in understanding the role of the CIB in cosmic evolution is the problem of distance and time. The light we are observing from these ancient galaxies has traveled for billions of years, meaning that we are seeing them as they were in the distant past. This introduces a time lag, making it difficult to directly observe the processes occurring in real time. However, by studying the redshift of the CIB, astronomers can determine the distance to these galaxies and estimate when they formed. This allows scientists to build a timeline of galactic evolution, helping to understand when the first stars and galaxies formed and how they contributed to the broader evolution of the universe. In addition to studying the formation of galaxies, the CIB also offers important clues about the role of dark matter in cosmic evolution. Dark matter is a mysterious substance that does not emit light and cannot be directly observed. However, its presence can be inferred by the way it influences the motion of galaxies and galaxy clusters. One of the key ways that dark matter interacts with the CIB is through its influence on the formation and distribution of galaxies. Because dark matter interacts with normal matter through gravity, it plays a crucial role in the structure formation of the universe. By studying the CIB, we can gain insights into the distribution of dark matter and its impact on galaxy formation. While the CIB is an invaluable tool for studying the early universe, it is important to acknowledge the limitations of this approach. The CIB represents a blended signal from many different sources, including stars, galaxies, dust, and gas clouds. This makes it difficult to separate the individual contributions of each source. Additionally, the signal-to-noise ratio of the CIB can vary depending on the region of the sky being observed. As a result, some regions of the CIB are easier to study than others, and much of the faint radiation from distant sources remains difficult to detect. Despite these challenges, advancements in infrared observatories and space telescopes continue to improve our ability to study the CIB in greater detail. One of the most promising developments in this field is the launch of the James Webb Space Telescope, JWST. This next-generation space telescope, which is designed to observe the universe in infrared wavelengths, is equipped with a suite of instruments capable of detecting the faintest signals from the distant universe. The JWST's advanced infrared capabilities will allow it to study the CIB with unprecedented precision, offering new insights into the early stages of cosmic evolution. By using JWST to observe the CIB, scientists hope to uncover new details about the formation of galaxies, the role of dark matter, and the processes that gave rise to the universe's current structure. Another important avenue of research is the study of the cosmic dawn, the period when the first stars and galaxies formed. The CIB holds valuable information about this critical period in the universe's history, which occurred roughly 13.5 billion years ago. During the cosmic dawn, the universe transitioned from being a dark, featureless expanse of hydrogen and helium to a vibrant, star-filled cosmos. This period of reionization is thought to have been triggered by the formation of the first stars and galaxies, which emitted ultraviolet radiation that ionized the surrounding gas. By studying the CIB, scientists can gain a better understanding of the timeline and processes involved in this dramatic transformation. As we look further into the universe's past, we begin to encounter the mysterious cosmic voids, vast expanses of space that are nearly empty of galaxies and other matter. These voids are thought to have formed early in the universe's history and may provide important clues about the distribution of matter in the cosmos. The CIB can help us study the edges of these voids and understand how they relate to the overall structure of the universe. These studies are crucial for understanding the large-scale structure of the universe and the forces that have shaped its evolution. At the same time, the study of the CIB is also advancing our understanding of the end of the cosmic dark ages. This period, which lasted from the end of the cosmic microwave background radiation to the formation of the first stars, was a time when the universe was nearly devoid of light. The CIB provides a window into this dark epoch, helping to bridge the gap between the universe's early, opaque state and its eventual transition to a cosmos filled with light and structure. The data gathered from the CIB will be instrumental in answering some of the most fundamental questions about the origins of the universe, including the nature of the first stars, galaxies, and cosmic structures. In addition to its scientific value, the study of the cosmic infrared background has broader implications for our understanding of the universe's ultimate fate. The CIB is a record of the universe's history, and by studying it, we can gain insights into the forces that are shaping the cosmos today. For example, the expansion of the universe, driven by the mysterious force of dark energy, has had a profound impact on the distribution of galaxies and the evolution of the cosmic structure. As the universe expands, the CIB continues to evolve, offering a glimpse into the future of cosmic evolution. By understanding the patterns of radiation in the CIB, scientists can develop models of the universe's fate and predict how it will continue to change over time. The cosmic infrared background is one of the most fascinating and informative aspects of modern cosmology. By studying this faint glow of radiation, scientists are unlocking the secrets of the early universe and gaining insights into the processes that shaped the cosmos. The CIB provides valuable clues about the formation of galaxies, the role of dark matter, and the evolution of the universe over billions of years. As new technologies and telescopes like the James Webb Space Telescope continue to advance, the study of the CIB will remain at the forefront of cosmological research, helping to answer some of the most profound questions about the origins and future of the universe. As we continue to explore the cosmic infrared background (CIB), we dive deeper into how this faint radiation informs us about the universe's distant past and its current evolution. The study of the CIB is not just a journey to understand the past, it's also a key to unlocking the future of the universe. As astronomers continue to refine their techniques for detecting and analyzing the CIB, new insights emerge that are reshaping our understanding of the cosmos. One of the primary challenges in studying the CIB is distinguishing between the various sources of infrared radiation that contribute to it. The infrared background light we observe today is a mixture of emissions from several sources. These sources include the afterglow from the Big Bang itself, radiation from early stars, galaxies, and even the emission from intergalactic dust. This complex blend of signals makes it difficult to isolate individual contributions, but recent advancements in infrared observatories have made it possible to detect the faintest signatures of distant cosmic events. By studying the faint, infrared light emitted by distant galaxies and star-forming regions, scientists can trace the evolution of the universe in detail. The CIB allows us to look further back in time than ever before, offering a glimpse into the cosmic dark ages, a period when the universe was still opaque and nearly void of stars. These early epochs are critical for understanding how the universe transitioned from a formless cloud of gas to the rich, structured cosmos we observe today. The cosmic infrared background plays a crucial role in revealing the time when the universe's first stars ignited, beginning the process of reionization that transformed the universe. As we look deeper into the universe, we encounter regions that are redshifted, meaning their light has been stretched to longer wavelengths as the universe expanded. This phenomenon has a direct impact on how we interpret the CIB. The further back in time we look, the more the light we observe is stretched out, and this stretching corresponds to a shift in the light from visible wavelengths into the infrared spectrum. The CIB, therefore, offers a way to observe redshifted light from the universe's earliest periods, allowing astronomers to study the formation of galaxies and star clusters at a time when they were still in their infancy. The study of infrared light is particularly valuable because it provides insights into some of the most obscured and hidden aspects of the universe. Stars and galaxies are often surrounded by dense clouds of dust and gas that absorb and scatter light, particularly in the visible spectrum. However, these materials are much more transparent to infrared radiation, allowing us to peer through these clouds and gain insights into regions that would otherwise be invisible to traditional optical telescopes. This ability to peer through cosmic dust is a critical advantage of studying the CIB, as it provides a clearer view of the universe's formation and evolution. The CIB is also a key tool in understanding the nature of dark energy and its role in the expansion of the universe. Dark energy is the mysterious force driving the accelerated expansion of the cosmos, but its precise nature remains elusive. By studying how the CIB has changed over time, scientists can gain insights into the influence of dark energy on the large-scale structure of the universe. This allows astronomers to refine their models of cosmic expansion and develop a better understanding of the forces that are shaping the universe's future. Moreover, the study of the CIB also provides a glimpse into the formation and evolution of large-scale structures in the universe. The earliest structures to form in the universe were not galaxies but rather clumps of gas and dark matter. These primordial clumps were the building blocks of galaxies, stars, and other cosmic structures. The CIB holds valuable clues about the interactions between these early cosmic structures, shedding light on how they merged and evolved into the galaxies and clusters of galaxies we see today. Understanding the origins of these structures is critical for understanding the universe's evolution and the formation of the first stars. Another aspect of the CIB that makes it such a valuable tool is its connection to cosmic reionization. This process, which occurred roughly 400 million years after the Big Bang, marked the transition from an opaque, hydrogen-dominated universe to one that was transparent and filled with light. The first stars and galaxies played a pivotal role in this transition, emitting ultraviolet radiation that ionized the surrounding hydrogen gas. This ionization allowed light to travel freely across the universe, making the cosmos transparent for the first time. The CIB captures the afterglow of this reionization process, providing astronomers with vital clues about how it unfolded and when it occurred. The study of the cosmic infrared background is also deeply intertwined with the concept of cosmic inflation. Cosmic inflation is a theory that suggests the universe underwent a rapid expansion in the first moments after the Big Bang. This inflationary period is believed to have shaped the universe's large-scale structure and laid the foundation for the distribution of galaxies and clusters of galaxies we observe today. By studying the CIB, scientists can search for subtle imprints of this early inflationary period, looking for evidence that might confirm or refute the theory. In addition to the direct scientific benefits, the study of the CIB also has profound philosophical implications. It forces us to confront the very nature of the universe itself, and our place within it. By exploring the faintest glimmers of light from the early universe, we are peering back in time to a moment when the cosmos was very different from the universe we know today. This journey into the past raises fundamental questions about the origins of the universe, the forces that shaped it, and the ultimate fate of all things. The faint light from the cosmic infrared background is more than just a cosmic relic. It is a window into the heart of the universe. As we continue to refine our tools for observing this faint radiation, we are uncovering the hidden history of the cosmos. The CIB is not just a curiosity, it is a treasure trove of information about the universe's past, present, and future. By studying it, we are not only learning about the formation of galaxies and stars, but we are also gaining a deeper understanding of the fundamental forces that have shaped the universe from the very beginning. In the future, the continued study of the CIB promises to yield even more groundbreaking discoveries. With advancements in telescope technology, particularly in the field of infrared astronomy, we can expect to observe even fainter and more distant sources of radiation. This will allow us to push the boundaries of our understanding even further, exploring the earliest moments of the universe with unprecedented clarity. The upcoming observations by the James Webb Space Telescope, JWST, in particular, are poised to revolutionize our understanding of the CIB and its role in cosmic evolution. Equipped with state-of-the-art infrared instruments, JWST will be able to study the CIB in greater detail than ever before, providing fresh insights into the universe's earliest epochs. As we continue to observe and study the CIB, one thing is clear: the universe is far more complex and mysterious than we ever imagined. The faint glow from ancient star-forming regions may seem like a subtle, almost inconspicuous signal, but it holds the key to understanding the most profound mysteries of the cosmos. The study of the CIB is one of the most exciting and rewarding fields of modern cosmology, and as technology continues to advance, the answers to some of the universe's greatest questions are likely to emerge from this faint, cosmic light. The cosmic infrared background is not merely a distant, invisible feature of the universe. It is a crucial piece of the puzzle of cosmic evolution. By studying the CIB, astronomers are piecing together the story of the universe's earliest moments and understanding how it transformed from a primordial state into the complex and vibrant cosmos we observe today. The insights gained from the CIB will continue to shape our understanding of the universe for generations to come, helping to answer some of the most profound questions about our origins and our place in the vast expanse of space. As we delve even deeper into the mystery of the cosmic infrared background CIB, it's crucial to consider its role in the context of our larger understanding of cosmology. The CIB is not just a remnant of the early universe. It is a record of the events and processes that shape the cosmos. This faint glow from ancient star-forming regions is much more than background noise. It's a vital signal, carrying information about the formation of galaxies, stars, and the very fabric of space-time itself. One of the most intriguing aspects of the CIB is its ability to trace the evolution of large-scale cosmic structures. The first galaxies, formed from the collapsing gas and dust that arose after the Big Bang, emitted infrared light as they began to shine. This radiation has traveled through space for billions of years, fading and stretching as the universe expanded. Today, it represents a snapshot of the early universe's composition and activity. By studying the CIB, scientists can infer how galaxies clustered together, how star formation proceeded, and how these processes influenced the evolution of the universe's large-scale structure. The study of the CIB also allows us to examine the interplay between galaxies and the surrounding intergalactic medium. The hot gas in between galaxies can emit infrared radiation, contributing to the overall CIB signal. This diffuse gas, known as the intergalactic medium, IGM, contains a mix of hydrogen, helium, and other elements that were once part of the stars and the galaxies themselves. Studying this component of the CIB gives astronomers insight into how galaxies influence the gas around them, and vice versa. This helps to fill in the gaps in our knowledge about how galaxies formed and evolved in the early universe. At the same time, the CIB provides a unique opportunity to study the first stars and black holes. These early objects were unlike anything we see in the universe today. The first stars, known as population 3 stars, were massive, hot, and short-lived. They played a pivotal role in reionizing the universe, turning it from a dark, neutral state into one filled with ionized gas. The light emitted by these stars contributed significantly to the CIB, and studying this radiation is one of the few ways to learn about the characteristics of population 3 stars. Similarly, the first black holes were likely born during this time, and their growth and activity may have left a detectable imprint in the CIB. Understanding these early objects is a key to unlocking the mysteries of the early universe and the processes that led to the formation of galaxies and supermassive black holes. Interestingly, the CIB also offers a window into the composition of the universe's dark matter. Though dark matter cannot be observed directly, it exerts a gravitational influence on galaxies and other cosmic structures. The CIB gives us indirect clues about how dark matter distributed itself in the early universe. In the dense regions of dark matter, galaxies formed more quickly, and star formation was more intense. By studying the CIB's fluctuations, astronomers can make inferences about the distribution of dark matter and how it influenced the development of the universe's structures. One of the most significant contributions of the CIB to modern cosmology is its connection to theories of cosmic inflation. Inflation is the theory that suggests the universe underwent a rapid expansion during the first moments after the Big Bang. This theory has revolutionized our understanding of the universe's early history, but many aspects of inflation remain speculative. The CIB offers a unique test for inflationary models. The faint radiation from the early universe holds subtle imprints of the inflationary period, patterns of temperature fluctuations, distortions caused by gravitational waves, and other phenomena that could provide evidence for or against the theory of inflation. As we continue to study the CIB, these imprints will help us refine our understanding of the universe's birth. The role of cosmic microwave background (CMB) radiation in cosmology cannot be overstated. The CMB is the afterglow of the Big Bang, a faint radiation that fills the entire universe and provides a snapshot of the universe when it was just 380,000 years old. This radiation, while incredibly important in cosmological studies, is not the only radiation that carries information about the universe's early history. The CIB extends the CMB's story forward in time, revealing the changes that occurred as the universe evolved. As we piece together the CIB and CMB, we gain a more complete picture of the universe's infancy and its subsequent development. The study of the CIB is still in its infancy, with many of the most exciting discoveries yet to come. The James Webb Space Telescope, JWST, launched in December 2021, is set to make major contributions to this field. Equipped with a suite of infrared instruments, JWST will be able to observe the CIB in greater detail than ever before. It will be able to detect infrared radiation from distant galaxies, star-forming regions, and the intergalactic medium with unprecedented clarity. With its advanced capabilities, JWST has the potential to unveil many of the universe's secrets hidden in the infrared wavelengths, providing fresh insights into the history of galaxies, star formation, and the first cosmic objects. Another promising avenue for studying the CIB lies in ground-based observatories. Despite the challenges posed by Earth's atmosphere, some ground-based telescopes are capable of observing infrared light from distant cosmic sources. These telescopes use advanced techniques like adaptive optics and interferometry to overcome atmospheric distortions and achieve high-resolution observations. In the coming years, ground-based telescopes, in collaboration with space-based observatories, will push the boundaries of our knowledge about the CIB and the universe's early history. The implications of studying the cosmic infrared background extend far beyond the realm of astronomy and physics. The insights gained from the CIB help to address fundamental questions about the origins of the universe, the nature of dark matter and dark energy, and the processes that led to the formation of galaxies and stars. The more we learn about the CIB, the more we uncover about the universe's origins and its eventual fate. The cosmic infrared background serves as a bridge between the past, present, and future of the universe, providing a unique glimpse into the forces that shaped everything we see today. As our technology advances and our methods of observation become more refined, we can expect even more exciting discoveries to emerge from the study of the CIB. The universe is far from static, and as we continue to probe its depths, we uncover new layers of complexity that challenge our existing theories and inspire new lines of inquiry. The CIB is just one of many pieces in the puzzle of the cosmos, but it is perhaps one of the most significant. By continuing to study this faint radiation, we are uncovering the hidden history of the universe, a history that stretches back billions of years and holds the answers to some of the most profound questions humanity has ever asked. The cosmic infrared background is a vital tool in our quest to understand the universe. It offers a unique and invaluable perspective on the formation and evolution of galaxies, stars, and cosmic structures. Through the study of the CIB, we gain insights into the early history of the universe, the nature of dark matter and dark energy, and the processes that shape the cosmos. The CIB is more than just a faint glow, it is a window into the past, a key to unlocking the mysteries of the universe, and a guide to the future of cosmology. As we continue to explore this cosmic phenomenon, we are bound to uncover more secrets that will deepen our understanding of the cosmos and our place within it. The cosmic infrared background, CIB, has already proven to be a game-changer in the realm of cosmology, but the questions it raises only continue to multiply. The more we study it, the more we realize that it's not just a faint afterglow of ancient star-forming regions. It is a conduit through which we can peer into the very foundations of our universe. As we move forward in our understanding, there are countless opportunities to refine existing models and potentially discover entirely new phenomena that challenge what we thought we knew about the cosmos. As we've discussed, the CIB is deeply connected to the early stages of galaxy formation. One of the central mysteries in cosmology is how galaxies formed out of the primordial soup of gas and dark matter that existed just after the Big Bang. This transition, from a featureless universe to one filled with galaxies, stars, and other cosmic structures, is known as cosmic structure formation. The CIB provides a glimpse into this transition, as it captures the energy released by the very first stars and galaxies that emerged from the primordial darkness. These early galaxies, although long gone, left behind a cosmic signature that still reverberates through space, allowing us to study their characteristics. The contribution of early stars, and the role they played in ionizing the universe, is a particularly fascinating aspect of CIB research. Shortly after the Big Bang, the universe was filled with neutral hydrogen atoms, creating what is known as the cosmic dark ages. During this period, no stars or galaxies had yet formed, and the universe was opaque to light. The first stars, population 3 stars, emerged from the gas clouds, and their radiation began to ionize the hydrogen atoms, turning the universe from an opaque fog into a transparent space in which light could travel freely. This process is referred to as Reionization, and its signature is embedded in the CIB. Studying this faint glow allows astronomers to investigate the timing and nature of reionization, providing insight into one of the most pivotal moments in the universe's early history. Another key element of the CIB that continues to captivate scientists is its potential to provide insight into the formation of supermassive black holes. These mysterious and incredibly dense objects, which reside at the centers of most galaxies, including our own Milky Way, are thought to have formed relatively soon after the Big Bang. The CIB contains faint traces of radiation emitted by the very first black holes, which were likely powered by the gas accreting onto them in the early universe. By studying this radiation, researchers hope to uncover details about how these early black holes grew so massive and how their presence influenced the galaxies around them. The interaction between these black holes and their host galaxies is still not well understood, but the CIB could provide valuable clues that could unlock the secrets of this relationship. While much of the CIB's story is tied to star formation, galaxies, and black holes, we must not forget its important connection to the distribution of dark matter. Dark matter, a mysterious substance that makes up about 85% of the total mass in the universe, is invisible to our current instruments. However, its gravitational effects are seen everywhere in the universe. The CIB provides indirect clues about how dark matter has shaped the development of the universe's large-scale structure. By analyzing fluctuations in the CIB, astronomers can trace the distribution of dark matter in the early universe, shedding light on how it influenced the formation of galaxies and clusters of galaxies. This, in turn, could help us better understand the elusive properties of dark matter and its role in the universe's evolution. As with many scientific endeavors, progress in understanding the CIB relies heavily on technological advancements. The James Webb Space Telescope, JWST, which has already begun its operations, is expected to make unprecedented contributions to this field. Equipped with the most advanced infrared sensors ever built, JWST will be able to study the CIB in ways that were previously unimaginable. Its ability to observe extremely faint infrared signals from the distant past will allow scientists to study galaxies, stars, and the intergalactic medium with greater precision and depth. Not only will this help us learn about the early universe, but it will also allow us to trace the evolution of galaxies and stars throughout cosmic history. With JWST's capabilities, we are on the cusp of a new era of discovery that could provide answers to questions that have puzzled scientists for centuries. But even with the incredible potential of JWST, the study of the CIB will remain a multifaceted challenge. The faint glow from ancient star-forming regions is extremely difficult to isolate from the background noise created by modern galaxies, interstellar dust, and other sources of infrared radiation. To solve this puzzle, astronomers employ a combination of techniques. One method is to use statistical analysis to separate the CIB's signal from other infrared emissions. By studying the fluctuations in the CIB, researchers can identify patterns that reveal its origin. Another approach is to combine data from multiple telescopes and observatories, both ground-based and space-based, to get a clearer picture of the CIB's characteristics. In addition to observational techniques, theoretical models play a crucial role in interpreting the CIB's signature. These models are based on our current understanding of how galaxies form, how stars evolve, and how the intergalactic medium behaves. However, as we gain more observational data, these models will need to be refined or even rethought in light of new discoveries. For example, the CIB could reveal unexpected features that suggest alternative theories about the early universe's development. As we continue to probe the CIB, it's likely that we will encounter new phenomena that challenge existing theories and lead to a deeper understanding of the cosmos. One of the most exciting possibilities of CIB research is its connection to multiverse theories. Some cosmologists believe that our universe may be part of a larger, possibly infinite, collection of universes known as the multiverse. While this idea remains speculative, the study of the CIB could provide some clues as to whether or not the multiverse theory is valid. If evidence of other universes exists in the form of unusual patterns or anomalies in the CIB, it could offer groundbreaking insights into the nature of reality itself. While this is still very much in the realm of speculation, it shows how the study of the CIB can push the boundaries of our understanding of the universe and our place within it. The cosmic infrared background is also crucial for understanding the cosmic dark energy that is driving the accelerated expansion of the universe. Dark energy, which makes up about 68% of the universe's total energy content, is one of the biggest mysteries in modern physics. The The CIB may hold subtle clues about the nature of dark energy, especially if its fluctuations reveal any connection between this mysterious force and the universe's structure. Understanding dark energy is one of the most significant challenges in cosmology, and the study of the CIB could play a crucial role in unlocking its secrets. In addition to all the aforementioned aspects, the cosmic infrared background also offers a way to test our understanding of the laws of physics at the most fundamental levels. The radiation from the early universe, as observed in the CIB, carries information about the physical constants and fundamental forces that govern the universe at its inception. By analyzing this radiation, scientists can test whether the laws of physics have remained constant over time, or whether they may have evolved. This could have profound implications for our understanding of space, time, and the fundamental nature of the cosmos. As we continue to explore the cosmic infrared background, we come closer to unlocking many of the universe's deepest secrets. The information that this faint glow carries is not just important for understanding the early universe, but it may also hold the keys to understanding the present and the future. The CIB is a window into a past that will forever shape the future of cosmology and the quest to answer some of the most profound questions in science. The exploration of the cosmic infrared background (CIB) is a monumental task that extends far beyond our current grasp. Yet, as technology improves, we are increasingly capable of uncovering the secrets embedded in this faint, ancient glow. In the near future, we can expect remarkable breakthroughs in our understanding of the universe's early years and the forces that shaped its evolution. The implications of these discoveries are not confined to theoretical physics or astronomy alone. They could have profound philosophical, cultural, and even existential consequences for how we view our place in the cosmos. One of the aspects of the CIB that has fascinated scientists for decades is its connection to the cosmic microwave background (CMB), which is often referred to as the afterglow of the Big Bang. The CMB, which we've discussed before, is the earliest remnant radiation that we can observe from the early universe, dating back to when the universe was just 380,000 years old. In contrast, the CIB represents the light from regions where stars and galaxies began to form, possibly hundreds of millions of years after the Big Bang. By studying both the CMB and the CIB, astronomers can create a more complete picture of the universe's early history, from the formation of the first atoms to the emergence of complex cosmic structures. These two pieces of cosmic radiation, in tandem, provide complementary insights that could fill in the gaps between the universe's birth and its subsequent development. What makes the study of the CIB particularly compelling is the interplay between light and matter in the early universe. When the first stars ignited, their radiation began to ionize the surrounding gas, which eventually led to the formation of galaxies. The CIB's radiation, a byproduct of this early star formation, allows us to measure how much gas was available for the formation of galaxies. Furthermore, by understanding the spectral properties of the CIB, we can determine the types of stars that were forming during this period. Were they large, short-lived stars, or smaller, longer-living ones? How did the environment influence the types of stars that formed? These questions could lead to a greater understanding of galaxy formation and the conditions that prevailed in the early universe. This area of research not only helps us trace the evolution of galaxies but also allows us to probe the nature of the intergalactic medium, the diffuse gas that fills the space between galaxies. The intergalactic medium is made up mostly of hydrogen and helium and is extremely hot and sparse. Despite its invisibility to the naked eye, its properties can be studied through the radiation that passes through it, including the CIB. Studying how this gas interacted with the radiation from early stars could help us understand how matter clumped together to form galaxies and how it was redistributed as the universe expanded. It's a delicate balance between gravitational attraction and the expanding force of the universe itself, and understanding how this interplay occurred in the early stages of the cosmos could provide us with the key to understanding how large-scale structures in the universe developed. The influence of supernovae, the explosive deaths of massive stars, on the formation of galaxies is another important element linked to the CIB. Supernovae release enormous amounts of energy, scattering heavy elements across the universe. These elements, such as carbon, oxygen, and iron, are crucial for the formation of planets, stars, and life itself. The CIB offers indirect evidence of these violent events by capturing the remnants of radiation from the supernovae that occurred in the early universe. By studying the patterns in the CIB, astronomers can estimate the frequency and intensity of supernovae in these ancient regions, providing vital information about the chemical enrichment of the universe. This process of metal enrichment is key to understanding how the universe transitioned from a sterile collection of hydrogen and helium to the rich, diverse environment we observe today. In recent years, the study of the CIB has become increasingly interconnected with research into extragalactic dust. Dust in the interstellar and intergalactic medium plays a pivotal role in the evolution of galaxies. It absorbs and scatters light, including the infrared radiation captured in the CIB, which can distort our observations. However, the same dust also emits radiation, contributing to the CIB itself. By studying the intricate relationship between the CIB and the presence of dust, astronomers can gain insights into the processes by which galaxies evolve. What is the role of dust in cooling gas, triggering star formation, or in the development of supermassive black holes? These are some of the most pressing questions that can be addressed by further studying the CIB. One aspect of the CIB that continues to remain elusive is its temperature. The CIB is composed of faint infrared radiation, but how hot was it when it was emitted by the first stars and galaxies? Understanding the temperature of the early universe, particularly the radiation emitted during the period of star formation, is crucial for estimating the size, scale, and distribution of galaxies. It is thought that the radiation from these early galaxies would have been much hotter than the CIB we observe today. With each successive wave of observations, scientists hope to get closer to answering the question, at what temperature did the universe's first stars shine? This question ties into broader inquiries about the physics of the early universe, including how radiation and matter interacted in the extreme conditions following the Big Bang. One of the more ambitious questions in the field of cosmology is whether the study of the CIB can provide us with clues about dark energy and dark matter. Dark energy, as we've discussed, is believed to make up around 68% of the universe's energy content, yet it remains invisible to current telescopes and detectors. By studying the fluctuations in the CIB, researchers are hoping to detect the subtle effects of dark energy on the large-scale structure of the universe. Similarly, the distribution of dark matter, which does not emit light but interacts gravitationally with visible matter, could also be traced through the study of CIB fluctuations. In many ways, the CIB serves as a bridge between what we can observe, stars, galaxies, black holes, and the unseen forces that govern the universe. In the quest to understand the CIB, next-generation telescopes will play an indispensable role. Instruments like the Atacama Large Millimeter Array, ALMA, and the James Webb Space Telescope offer unprecedented sensitivity to infrared radiation. These telescopes allow us to probe the CIB with unparalleled precision, unlocking details about the universe's infancy that were previously out of reach. Moreover, upcoming missions and observatories, such as the Planck Space Telescope, aim to provide even more detailed measurements of the cosmic infrared background, providing clearer data on its structure and evolution. In the future, the study of the CIB may not just be limited to understanding galaxy formation or star evolution. As our observational tools improve, we could begin to use the CIB as a tool for studying the very nature of time and space itself. The radiation captured in the CIB could offer clues about the geometry of the universe, possibly revealing distortions in space-time caused by gravitational waves or interactions with hidden dimensions. These theories remain speculative, but the idea that the CIB could serve as a probe for such phenomena is a tantalizing possibility that could reshape our understanding of the universe on its most fundamental level. As we peer deeper into the cosmic infrared background, we stand at the threshold of some of the most profound discoveries in science. Every breakthrough brings us closer to understanding the origin of galaxies, the formation of the first stars, and the nature of the universe itself. The faint glow from the distant past may hold the answers to questions that have intrigued humanity for centuries, questions about the beginning of everything, the nature of dark matter and energy, and the future of the cosmos. What is certain is that the study of the CIB is not just about understanding the past, it is also about unlocking the future. As the study of the cosmic infrared background, CIB, continues to unfold, it opens a doorway to some of the most profound mysteries in modern cosmology. Beyond the mere investigation of the early universe's structure, the CIB could offer a glimpse into the very nature of the cosmos itself. Through this study, we may uncover insights into the origin of galaxies, the processes that led to the formation of the first stars, and the unseen forces that shaped the universe as we know it. Each discovery brings us closer to answering the age-old questions about our place in the universe, the forces that drive its evolution, and what might lie beyond the observable universe. A key element of this exploration is the understanding of how light interacts with the universe's expanding fabric. The expansion of the universe stretches out the wavelengths of light emitted by distant sources, shifting their wavelengths into the infrared spectrum. This redshift process is especially evident in the faint glow of the CIB. By studying these redshifts, we can learn more about the rate at which the universe has expanded over time, shedding light on the history of cosmic acceleration. This could also allow us to probe the behavior of dark energy, the mysterious force that is driving the accelerated expansion of the universe. The importance of the CIB as a diagnostic tool cannot be overstated. With its ability to carry information from distant epochs, the CIB provides a unique opportunity to directly observe the conditions that prevailed during the formative stages of the universe. For instance, the study of the CIB can offer valuable insights into the Reionization epoch, a period when the universe transitioned from being opaque to transparent. This event, which occurred roughly 1 billion years after the Big Bang, marked the moment when the first stars and galaxies began to ionize the surrounding hydrogen gas, allowing light to travel freely across the universe. Understanding the role of the CIB in this process is crucial for piecing together the story of the universe's early evolution. At the heart of this investigation lies the question of how early star formation influenced the growth of the first galaxies. As we've seen, the CIB represents the cumulative effect of all the star-forming activity that occurred during the universe's early epochs. The light captured by the CIB is not just a snapshot of isolated stellar events, it is the sum of countless interactions between stars, gas, dust, and radiation. Through the study of the CIB, we can gain a detailed understanding of how the first galaxies came together, and how their growth may have influenced the development of the universe as a whole. Additionally, the CIB offers an unparalleled view into the formation and evolution of cosmic structures. It provides an observable connection between the dark matter halos that surround galaxies and the light emitted by the stars within those galaxies. Dark matter, though invisible to us, exerts a powerful gravitational influence on the visible matter in the universe. This influence shapes the distribution of galaxies and other large-scale structures in the cosmos. By studying the CIB, we can probe the interactions between dark matter and ordinary matter, revealing the underlying structure of the universe. The intricate relationship between light and dark matter is one of the key mysteries that the CIB could help us solve. In this context, the role of galaxy clusters becomes particularly significant. Galaxy clusters, the largest gravitationally bound structures in the universe, are made up of hundreds or even thousands of galaxies. These clusters are often located in areas of the universe where the CIB is most intense, due to the dense concentrations of stars and gas. By examining the CIB in and around these galaxy clusters, astronomers can glean insights into the formation and evolution of these massive structures. Understanding how galaxy clusters evolve over time could provide valuable clues about the nature of large-scale cosmic evolution, the behavior of matter on the largest scales, and how galaxies are interconnected within the vast expanse of space. Another fascinating aspect of the CIB is its potential connection to the elusive phenomenon known as cosmic inflation. Cosmic inflation refers to the rapid, exponential expansion of the universe that is thought to have occurred during the first fractions of a second after the Big Bang. This event is believed to have set the stage for the large-scale structure of the universe that we observe today. Some theorists believe that the study of the CIB could offer indirect evidence for cosmic inflation by revealing imprints left by the inflationary era in the form of subtle fluctuations in the infrared radiation. These imprints, known as B-modes, are thought to carry signatures of gravitational waves from the early universe, and detecting them would represent a major breakthrough in our understanding of the universe's origins. Moreover, As we continue to explore the CIB, we are also presented with the possibility of discovering new types of exotic phenomena that could challenge our current understanding of physics. The early universe, in all its complexity, was a time of intense and chaotic processes, with forces and energies that are not fully understood even today. Some scientists speculate that the CIB might contain traces of unknown, exotic matter or energy, perhaps revealing aspects of the universe that were once hidden from view. In this sense, the study of the CIB could open the door to new realms of discovery, providing us with glimpses of a reality far beyond the standard model of cosmology. Of course, none of this progress would be possible without the advancements in observational technology that have made the study of the CIB possible. Instruments like the Hubble Space Telescope and the Spitzer Space Telescope have already provided us with stunning views of the infrared universe, but their capabilities are limited by their sensitivity and the inherent difficulty of observing such faint radiation. This is where future missions, such as the James Webb Space Telescope, come into play. Webb's cutting-edge instruments are designed to peer even further into the distant reaches of the universe, capturing the faintest infrared light from the earliest galaxies. With its ability to detect infrared radiation with unprecedented accuracy, Webb will likely revolutionize our understanding of the CIB and offer new insights into the universe's evolution. Beyond telescopes, other technological innovations, such as advanced computational modeling and simulations, are helping to interpret the data we collect from the CIB. These models allow us to simulate the conditions of the early universe, testing different theories of galaxy formation, star evolution, and dark matter interactions. By comparing these simulations with actual observational data, scientists can refine their models and develop a more accurate picture of the universe's history. The interplay between theory and observation is what drives progress in this field, and it is through this synergy that we can hope to unlock the deepest secrets of the universe. The cosmic infrared background represents one of the most promising frontiers in the study of the universe. It offers a window into the distant past, revealing the early stages of galaxy formation, the birth of stars, and the intricate relationships between light, matter, and the fabric of space-time. As we continue to probe the CIB with next-generation telescopes and advanced computational techniques, we are poised to make groundbreaking discoveries that could reshape our understanding of the cosmos. From unraveling the mystery of dark matter to uncovering the secrets of the universe's earliest moments, the study of the CIB holds the key to answering some of the most profound questions in cosmology. The universe, vast and full of hidden mysteries, continues to inspire awe and wonder. As we continue our quest for knowledge, each new discovery brings us closer to understanding the forces that shape the cosmos and our place within it. The CIB may very well be the key to unlocking the ultimate secrets of the universe, offering insights into the origin, evolution, and future of everything that exists. With every step forward, we inch closer to unveiling the deep, interconnected story of the universe, one that stretches back to its earliest moments and reaches out into its unimaginable future. As we dive deeper into the study of the cosmic infrared background (CIB), it becomes evident that its significance goes beyond simply providing insight into the early universe's star formation and galaxy development. It serves as a cosmic time machine, taking us back to an era when the universe was still in its infancy, a time when light itself was struggling to emerge from the darkness. The study of the CIB holds the potential not just to answer questions about the history of the universe, but also to shed light on phenomena that remain as elusive and mysterious as the universe itself. One of the most intriguing aspects of the CIB is its role in understanding the large-scale structure of the universe. By studying the faint infrared radiation from distant galaxies and star-forming regions, scientists can gain insights into the way that matter has been distributed across the cosmos. The CIB essentially captures the sum of all the energy emitted by these early galaxies, and by analyzing the intensity and distribution of this radiation, we can make inferences about the cosmic web, the vast network of galaxies, clusters, and filaments that make up the large-scale structure of the universe. Through this process, astronomers can trace the growth and evolution of galaxies and the interconnected web of dark matter that binds them together. The cosmic web is a fundamental structure in our understanding of the universe. It consists of vast cosmic voids and dense clusters of galaxies interconnected by long strands of dark matter. The CIB provides one of the best ways to map this structure, as the radiation emitted from early galaxies and star-forming regions often interacts with the surrounding dark matter. By observing the patterns of infrared radiation, scientists can begin to unravel how these massive structures came into being. It is through the study of the CIB that we can piece together the history of the cosmic web and understand how galaxies and other structures formed and evolved over time. In particular, the study of galaxy formation is intricately tied to the investigation of the CIB. The faint infrared light that we observe from distant galaxies is primarily the result of star formation and the subsequent emission of energy by those stars. As stars form, they heat the surrounding gas and dust, causing it to emit infrared radiation. This radiation, while faint, carries with it critical information about the processes occurring within these galaxies, such as how stars are born, how they evolve, and how they interact with the surrounding environment. This is particularly important when considering the formation of the first galaxies, those that existed when the universe was still in its early stages, less than 1 billion years old. When we observe the CIB, we are essentially looking at the aftermath of the formation of these first galaxies. The radiation that we detect today is a remnant of the stellar activity that occurred long ago, and by studying it, we can reconstruct the process of galaxy formation itself. This is critical for answering questions about how galaxies like our own Milky Way came to be. Were they formed in a relatively quiet and gradual process, or did they experience rapid bursts of star formation? The CIB offers a means of understanding these fundamental questions, providing insight into the forces that shaped our universe. Beyond the more familiar topic of galaxy formation, the CIB also provides a unique window into the study of exotic phenomena, such as the formation of the first black holes. It is believed that the formation of supermassive black holes occurred in tandem with the development of early galaxies. These black holes likely began as smaller stellar mass black holes and grew through a process known as accretion, where they pull in gas and other matter from their surroundings. As this material falls into the black hole, it emits energy, often in the form of X-rays, which then interacts with the surrounding infrared radiation. By studying the CIB, we can gain valuable information about the birth of these supermassive black holes and their role in shaping the formation of galaxies. Additionally, the CIB has the potential to provide answers to questions about the nature of dark energy. Dark energy is a mysterious and largely unknown force that is believed to be responsible for the accelerated expansion of the universe. Though it has been postulated for decades, the precise nature of dark energy remains elusive. By studying the CIB and the behavior of infrared radiation, scientists can learn more about how the expansion of the universe has evolved over time and, in doing so, gain a better understanding of the role that dark energy plays in this process. This could help us unravel one of the greatest mysteries of modern cosmology: what is driving the accelerated expansion of the universe? Furthermore, the interplay between light and dark matter is another intriguing aspect of the CIB. Dark matter, which constitutes a significant portion of the universe's total mass, is invisible to direct observation, but its presence is inferred through its gravitational effects on visible matter. The CIB provides us with a unique opportunity to study the interactions between dark matter and visible matter, as the faint infrared light from distant galaxies is influenced by the presence of dark matter. By observing these interactions, scientists hope to gain deeper insights into the properties of dark matter, such as its density, distribution, and behavior across the universe. This is crucial for developing a more complete understanding of the fundamental forces that govern the cosmos. The study of the CIB is also crucial for understanding the epoch of Reionization, a critical period in the universe's history when the first stars and galaxies began to emerge, ionizing the neutral hydrogen gas that filled the universe and allowing light to travel freely. This epoch occurred roughly 1 billion years after the Big Bang, and it marked the end of the so-called cosmic dark ages, a time when the universe was opaque and unable to support the propagation of light. The CIB provides us with a glimpse into this period, offering clues about how the first stars formed and how they began to ionize the surrounding gas. By studying the CIB, we can begin to answer important questions about the conditions that led to the emergence of these early galaxies and their role in shaping the universe's structure. One of the most challenging aspects of studying the CIB is the difficulty of observing such faint radiation. The infrared light emitted by distant galaxies and star-forming regions is incredibly weak by the time it reaches us. Additionally, this radiation is easily drowned out by other sources of infrared light, such as the Earth's atmosphere, which is not transparent to infrared light. This means that in order to observe the CIB, scientists must rely on space-based telescopes that can observe the infrared universe without interference from Earth's atmosphere. The Hubble Space Telescope and the Spitzer Space Telescope have already made significant contributions to this field, but the upcoming launch of the James Webb Space Telescope promises to take our ability to study the CIB to unprecedented levels. The James Webb Space Telescope, JWST, scheduled for launch in the near future, is designed to observe the universe in the infrared spectrum with far greater sensitivity and resolution than any previous telescope. With its powerful instruments, the JWST will be able to peer even further into the early universe, studying the faintest infrared light from distant galaxies and providing insights into the processes that led to the formation of the first stars and galaxies. Its advanced capabilities will make it an essential tool for understanding the CIB and its role in the larger cosmic picture. As we look to the future, the study of the CIB will likely play a central role in answering some of the most profound questions in cosmology. It is through this faint infrared light that we will be able to peer into the heart of the universe's history, unlocking clues about the formation of galaxies, stars, black holes, and the mysterious forces that shape the cosmos. With each new discovery, we come closer to understanding the story of the universe, from its beginnings in the Big Bang to its continued expansion and the unknown mysteries that lie ahead. Ultimately, the CIB is more than just a cosmic relic. It is a gateway to understanding the forces that have shaped the universe over billions of years. It allows us to probe the very origins of light and matter, offering glimpses into a time when the universe was still young and in the process of evolving into the vast, complex cosmos that we see today. Through the study of the CIB, we may one day uncover the answers to some of the most enduring mysteries of space, and perhaps even discover new forces and phenomena that we have yet to imagine. The Cosmic Infrared Background (CIB) represents a unique opportunity for scientists to look back at a critical moment in the universe's history, one that predates even the formation of the first galaxies and stars. The light we now observe, so faint and distant, is a direct consequence of the cosmic events that unfolded more than 13 billion years ago. To fully appreciate its importance, it's essential to understand that the study of this faint light is more than just observing distant objects. It's about unraveling the very origins of structure in the universe itself. This is where the CIB stands out as a treasure trove for cosmologists and astrophysicists seeking to uncover the universe's deep past. In recent years, the study of the CIB has moved from an abstract theory to a rapidly developing field of research. Many questions remain, and each discovery only seems to deepen the intrigue. One major question scientists are trying to answer is, what were the earliest stages of star formation like? The CIB contains echoes of that process, but because it is spread out over vast distances, much of the data we rely on is indirect. This means scientists have had to develop complex models to interpret what the faint glow of the infrared background really means about the early universe. One fascinating aspect of the CIB is that it is a blend of many different cosmic eras. Some of the infrared radiation we see today originated during the epoch of Reionization, while other light may be the result of ongoing star formation in galaxies that were forming just a few billion years after the Big Bang. Still, some of the light might be coming from even earlier times, originating from the very first stars that began to illuminate the cosmos. The complexity of this mixture is what makes the study of the CIB so challenging and so exciting. By carefully studying the wavelengths and intensity of the radiation, scientists are beginning to sort out which parts of the CIB correspond to which time periods in the universe's history. But why is this radiation so important? The answer lies in the fact that the formation of the first stars and galaxies was one of the most important transitions in cosmic history. Before this, the universe was in a state known as the Cosmic Dark Ages, a period when the universe was filled with neutral hydrogen gas, and no stars or galaxies existed. It wasn't until the first stars began to form that the universe transitioned from this dark state to one in which light and structure could emerge. This process of reionization, where light began to break apart the hydrogen gas, was a pivotal event, and the CIB is the signature of that transition. Studying the CIB allows scientists to probe the era of reionization and explore when and how this major event occurred. By observing how the radiation is distributed across the sky and how it interacts with different elements, astronomers can reconstruct the timeline of reionization and gain a deeper understanding of the role played by early galaxies and stars in this process. It helps us answer questions like, how long did the reionization process take? And what were the conditions like in the universe when it was transitioning from being opaque to transparent? Moreover, the CIB is not just a relic of the early universe. It also provides us with a critical link between the early and later universe. As galaxies evolved, the processes of star formation, gas accretion, and black hole growth became more pronounced. Over time, these early star-forming regions gave rise to the galaxies we see today. By studying the CIB, we can better understand how early galaxies contributed to the larger structure of the universe, and how the energy released from those stars shaped the cosmos in the billions of years that followed. This brings us to one of the most compelling aspects of the CIB, the possibility of learning about early supermassive black holes. These objects are believed to have formed relatively soon after the Big Bang, likely growing rapidly by accreting matter from the surrounding gas. Their existence is still somewhat mysterious, as we can only infer their presence based on their gravitational influence and the radiation they produce. However, the CIB can give us important clues about how these black holes evolved and the role they played in shaping the growth of galaxies. The light emitted by these black holes interacts with the surrounding infrared radiation, and studying this interaction may help us piece together the timeline of their formation and growth. As technology advances, so too does our ability to observe the universe in new ways. The advent of powerful instruments like the James Webb Space Telescope, JWST, has revolutionized our understanding of the universe. JWST's ability to observe the universe in infrared wavelengths with unprecedented clarity will allow it to study the CIB with unmatched precision. It will help scientists map the distribution of early galaxies, track their evolution, and possibly even discover new cosmic phenomena. JWST will also be able to detect faint signals from distant quasars and galaxies that emit radiation at the wavelengths corresponding to the CIB. With this new level of sensitivity, astronomers will have the tools they need to answer fundamental questions about the universe's earliest moments. Another way the CIB is useful is in its potential to reveal new information about the composition of the universe. For years, scientists have been grappling with the mystery of dark matter and dark energy. The CIB is thought to carry information about both of these elusive components. For example, dark matter, though invisible, affects the distribution of galaxies and clusters. By studying the CIB, scientists can infer the presence and influence of dark matter based on how it interacts with the infrared light from galaxies and other cosmic objects. Similarly, dark energy, the mysterious force believed to be driving the accelerated expansion of the universe, may leave behind imprints in the CIB that scientists can detect and study. Perhaps one of the most exciting prospects of CIB research is the potential to discover entirely new phenomena that we haven't even imagined. Every time we push the boundaries of our observational technology, we uncover new mysteries and phenomena that challenge our understanding of the cosmos. It is possible that the faint, infrared light from the CIB could reveal new types of stars, galaxies, or even entirely new forms of matter or energy. The possibilities are endless, and each new observation takes us one step closer to unlocking the secrets of the universe. We've only just begun to scratch the surface of what the cosmic infrared background can tell us. Its study is one of the most exciting frontiers in modern astronomy, offering insights not just into the early universe, but into the fundamental forces that govern the cosmos. As technology improves and our understanding deepens, the CIB will continue to be a crucial tool in piecing together the puzzle of our universe's origin and evolution. By exploring the faint infrared glow from the earliest galaxies, star-forming regions, and the aftermath of the Big Bang, we are opening a window into a time when the universe was young and full of potential. The CIB is not just a relic from the past, it is a key to unlocking the future, as we continue to explore the vastness of space and our place within it. In the coming years, we can expect to uncover even more mysteries hidden within the depths of the cosmic infrared background. Perhaps we will finally answer the most pressing questions that have eluded us for so long. What happened during the first few 100 million years after the Big Bang? What role did the first galaxies and stars play in shaping the universe? And ultimately, what does the study of the CIB reveal about the nature of dark energy, dark matter, and the ultimate fate of the universe itself? The pursuit of these answers is one of the most exciting and profound scientific endeavors of our time. And with each new discovery, we edge closer to understanding the true nature of the universe, how it began, how it evolved, and where it is headed. The study of the cosmic infrared background, CIB, continues to yield some of the most exciting possibilities for discovery in the realm of astrophysics. As we delve deeper into this mysterious glow from the distant past, we find ourselves facing questions that challenge not only our understanding of space but also the fundamental laws of physics. What began as a faint signal has evolved into a complex tool, allowing scientists to explore epochs of cosmic history that were previously inaccessible. One area that has sparked significant interest is the connection between the CIB and the formation of the first stars and galaxies. The faint infrared radiation we observe today carries with it the signature of the universe's early star-forming regions. By studying this radiation, we can gain insights into the conditions that led to the birth of galaxies. These early galaxies were not like the ones we see today. They were much smaller, less structured, and filled with gas that was yet to form the stellar objects we are familiar with. The CIB offers a way to probe this era, a time when the universe was young and filled with a chaotic, dynamic process of formation. Researchers are particularly interested in understanding how these first galaxies formed and whether they behaved differently from the ones we observe today. The infrared radiation from the CIB helps us study the complex interplay between gas and dark matter in these early galaxies, giving us a glimpse into the dynamics of their formation. Did these galaxies form quickly, or was it a gradual process? What triggered the formation of the first stars? And how did their birth affect the surrounding gas and dark matter? These questions are central to our understanding of how the universe evolved from a featureless, homogeneous state into the diverse collection of galaxies, stars, and planets we observe today. At the same time, the CIB provides important clues about the large-scale structure of the universe. By mapping the distribution of the infrared background across the sky, scientists can get a sense of how matter is distributed on cosmic scales. This, in turn, allows us to explore the relationship between dark matter and ordinary matter in the early universe. How did dark matter clump together, and how did its interaction with normal matter influence the formation of the first galaxies? The CIB is a unique tool in answering these questions, as it reflects the conditions under which both dark and visible matter coexisted in the early universe. As our understanding of the early universe grows, so does the importance of the CIB in helping to answer some of the most profound questions in astrophysics. One such question revolves around the epoch of Reionization, a period when the universe transitioned from being opaque to transparent. During this time, the first stars and galaxies began to shine, their light ionizing the surrounding hydrogen gas and allowing photons to travel freely through space. This marked the end of the cosmic dark ages. Understanding the details of this transition is crucial to our comprehension of how the universe evolved from a primordial soup of particles into the cosmos we see today. The CIB, as a remnant of that era, provides valuable information about the timing and nature of reionization. The CIB also plays a crucial role in the ongoing search for cosmic inflation. This is the theory that the universe underwent an enormous expansion in the first few moments after the Big Bang, growing exponentially in size in a fraction of a second. The implications of this theory are profound, as it suggests that the large-scale structure of the universe may have been influenced by quantum fluctuations that occurred during inflation. By studying the tiny temperature variations in the CIB, scientists can test models of inflation and determine whether they accurately predict the observed properties of the universe. If successful, these tests could provide direct evidence for inflation, revolutionizing our understanding of the origins of the universe. Another area where the CIB holds great promise is in the search for exoplanets. While most exoplanet research focuses on detecting planets around nearby stars, the CIB offers a different approach. By studying the infrared radiation emitted by distant galaxies, astronomers may be able to detect the presence of exoplanets in the early universe, long before the first stars formed. These exoplanets would likely be very different from those in our own galaxy, and studying them could provide insights into the types of planets that existed during the universe's infancy. Could these early exoplanets support life, or were they too hot and hostile to sustain any form of life as we understand it? The answers to these questions remain elusive, but the CIB may hold the key to unlocking this mystery. The James Webb Space Telescope, JWST, is set to revolutionize our ability to study the CIB. Its unprecedented sensitivity in the infrared wavelength range will allow it to detect even the faintest traces of the CIB, providing us with the most detailed map of the early universe ever created. As JWST begins its mission, it will observe distant galaxies, quasars, and other cosmic phenomena, all while gathering data on the infrared background. With its powerful instruments, JWST will be able to measure the distribution of light in the CIB with greater precision than ever before, opening up new avenues for discovery. One of the most exciting possibilities offered by JWST is the potential to detect the first galaxies that formed after the Big Bang. These galaxies, which are still beyond the reach of current telescopes, are believed to have been crucial in the process of reionization. Their light would have filled the universe with radiation, gradually ionizing the hydrogen gas and allowing it to form the stars and galaxies we see today. JWST's infrared sensitivity will allow it to peer into the deepest reaches of space and time, providing a glimpse of these earliest galaxies and shedding light on their role in shaping the universe. Beyond just studying galaxies, JWST's capabilities will allow astronomers to probe the environment of early black holes. These supermassive black holes are thought to have formed very early in the universe's history, possibly growing rapidly in the first few billion years. Their growth may have been linked to the formation of early galaxies, and studying their radiation, particularly in the infrared spectrum, could provide important clues about how these black holes evolved and influenced their surrounding environments. This could help answer long-standing questions about the relationship between galaxies and their central black holes, and whether this relationship was present from the very beginning. The potential for new discoveries in the study of the CIB is vast, and the implications are far-reaching. Each new piece of data brings us closer to understanding the universe's infancy, and the processes that led to the formation of the cosmos as we know it. The CIB, with its faint and elusive radiation, may one day reveal answers to some of the most fundamental questions about the nature of the universe, from the first stars to the mysterious dark energy that drives its expansion. As we continue to observe and study the faint glow from the early universe, we are not just looking at distant objects, we are looking into the past. The light we see today is a snapshot of the universe when it was a mere fraction of its current age. By analyzing this light, we are piecing together a puzzle that spans billions of years and encompasses the most profound events in the history of the universe. The study of the CIB will likely remain one of the most exciting frontiers in astronomy for many years to come, as it promises to reveal not only the history of our cosmos but also the ultimate fate of the universe itself. As we continue to probe the cosmic infrared background (CIB), it's crucial to explore how this faint glow could potentially help us unlock more about the distant epochs of the universe. Understanding the interplay of matter, radiation, and dark energy in the early universe is no simple feat, but as new technologies emerge, the mysteries behind this cosmic radiation become increasingly clearer, offering us a glimpse into the universe's infancy. One exciting aspect of the study of the CIB is its connection to star formation. The first stars, which were likely massive, short-lived, and intense, are believed to have played a pivotal role in shaping the early universe. They not only helped to reionize the universe but also contributed to the creation of heavy elements, essential for the formation of planets and life. These early stars released vast amounts of ultraviolet and infrared radiation, which contributes significantly to the CIB we see today. Their radiation heated up the gas surrounding them, pushing it out of dense, star-forming regions and into the larger, colder regions of space. This process of heating and scattering is a key feature of the CIB, and by studying it, we can understand the mechanisms that allowed the first stars to form and evolve. However, despite the wealth of data being gathered, many challenges remain. The CIB is incredibly faint, and distinguishing it from other cosmic radiation can be like searching for a needle in a haystack. But advanced telescopes, like the James Webb Space Telescope, JWST, are designed to observe just this type of radiation. JWST's infrared capabilities will allow astronomers to look back in time, nearly to the very beginning of the universe, providing a detailed map of the CIB's distribution across the sky. These measurements could provide insights into how galaxies first came together and the conditions that led to their growth. Furthermore, the CIB also allows us to study the complex role that dark matter plays in the evolution of the cosmos. While dark matter remains invisible and elusive, its gravitational effects can be observed through the way it influences the distribution of galaxies and gas. The CIB is one of the few methods available to examine the behavior of dark matter at large cosmic scales. By analyzing the faint glow from distant star-forming regions, scientists can gain valuable information about how dark matter interacts with visible matter in the early universe. This could help us understand why galaxies are distributed the way they are and how their structures formed. As astronomers refine their techniques for studying the CIB, they are also diving deeper into the epoch of Reionization, a key period in the universe's early history. During this time, the first stars and galaxies began emitting enough ultraviolet radiation to ionize the hydrogen that filled the universe, allowing light to travel freely. The exact timeline of this process is still a matter of intense debate, but the CIB provides an important clue. The CIB's spectrum can be used to trace the progression of reionization, helping scientists understand when the first galaxies began to form and how their radiation impacted the surrounding universe. As we improve our observational tools, such as those provided by JWST, we expect to gain even greater insights into the detailed timeline of reionization. Another avenue of exploration involves cosmic inflation, the theory that the universe expanded exponentially just moments after the Big Bang. Cosmic inflation offers an explanation for why the universe is so homogeneous and isotropic on large scales. It's thought that the rapid expansion of space stretched tiny quantum fluctuations into the large structures we observe today. The CIB provides a unique tool for testing these theories. By studying the small-scale variations in the CIB's temperature, astronomers can detect the imprints of inflationary processes that took place in the universe's first moments. These variations could potentially be used to confirm or challenge existing models of cosmic inflation, providing critical information about the very foundations of the universe itself. The study of the CIB could also lead to breakthroughs in understanding the nature of dark energy, the mysterious force responsible for the accelerating expansion of the universe. Dark energy's effects are evident in the large-scale structure of the universe, as galaxies appear to be moving apart at an accelerating rate. Although much of dark energy's properties remain unknown, it is believed to play a significant role in shaping the evolution of the universe. By investigating the distribution and properties of the CIB, astronomers may uncover subtle clues about how dark energy has influenced the growth of galaxies and the formation of cosmic structures. This could eventually help answer the fundamental question: what exactly is dark energy, and how does it affect the universe on the largest scales? In addition to its theoretical significance, the CIB has practical applications in exoplanet studies. While most exoplanet research has focused on nearby stars, the CIB presents a unique opportunity to study the conditions of the early universe. For instance, by analyzing the infrared radiation emitted by distant star-forming regions, astronomers could detect the faint signatures of exoplanets in these ancient galaxies. These exoplanets would likely be very different from those in our own galaxy, and their study could provide crucial insights into the diversity of planetary systems in the early universe. Could these early planets have harbored life, or were the conditions too extreme for anything resembling life as we know it? The answers to these questions remain elusive, but the potential for discovery is immense. The James Webb Space Telescope, JWST, promises to be a game-changer in this field. With its unprecedented infrared capabilities, JWST will be able to map the cosmic infrared background with a level of detail previously unimaginable. The telescope's ability to observe in the infrared will allow it to peer deeper into the universe, uncovering galaxies and stars that are currently hidden from view. This will give us a clearer picture of the universe's early stages, shedding light on how the first galaxies and stars came into being. As JWST begins its mission, it will provide a treasure trove of data that will help answer many of the most profound questions in cosmology. In the coming years, we can expect new discoveries to emerge from these observations. Whether it's understanding the formation of the first galaxies, learning about the epoch of reionization, or investigating the role of dark matter and dark energy, the study of the CIB will continue to provide us with valuable insights into the history and evolution of the universe. As our tools and techniques evolve, so too will our understanding of the universe's earliest moments. Each breakthrough brings us closer to answering the most fundamental questions in cosmology. How did the universe begin? What processes shaped its early development? And what mysteries lie ahead as we continue to look further back in time? The CIB is more than just a faint glow in the sky. It is a window into the past, a relic of the universe's earliest days that holds clues to the formation of galaxies, stars, and planets. By studying the cosmic infrared background, we are peeling back the layers of the universe's history, uncovering secrets that have been hidden for billions of years. With new technologies and improved observational techniques, we are entering an exciting era of discovery that will reshape our understanding of the cosmos. As we continue to delve into the mysteries of the cosmic infrared background (CIB), it's essential to consider its broader implications for our understanding of the early universe. The CIB provides an invaluable tool for probing the first stages of cosmic history, a time when the universe was just beginning to take shape. Understanding how the first stars and galaxies formed and evolved not only helps us comprehend our own cosmic origins but also sheds light on the broader forces at play in the universe. Each discovery in this area brings us closer to answering the deepest questions about our existence and the fundamental nature of reality. One of the most fascinating aspects of the CIB is its ability to illuminate the process of galaxy formation. In the early universe, galaxies were far different from the familiar spiral and elliptical galaxies we see today. Instead, these primordial galaxies were likely small, irregular, and far more chaotic in their structure. The CIB acts as a cosmic map, revealing the distribution and properties of these early galaxies, allowing scientists to trace their evolution over time. By examining the CIB's faint glow, researchers can determine when and where the first galaxies began to form, offering clues about the conditions that allowed galaxies to grow and mature into the massive structures we observe in the modern universe. In addition to its role in galaxy formation, the CIB also plays a crucial role in our understanding of cosmic reionization. This period in the universe's history, occurring roughly 1 billion years after the Big Bang, marked the end of the cosmic dark ages. During this time, the universe was filled with neutral hydrogen gas, which absorbed and scattered light. The first stars and galaxies began emitting ultraviolet radiation, ionizing the surrounding hydrogen and allowing light to travel freely across the cosmos. The CIB provides a detailed record of this process, offering insights into how quickly and efficiently reionization occurred, as well as the regions of the universe where it happened first. The study of the CIB also intersects with our understanding of cosmic dust. Dust, despite its seemingly insignificant role in the vastness of space, is actually a critical component of galaxy evolution. As stars form and die, they produce vast quantities of dust, which accumulates in galaxies and contributes to the CIB's faint glow. This cosmic dust not only affects the way light travels through space but also plays a role in cooling gas clouds, which is essential for the formation of new stars. By studying the CIB and its relationship with cosmic dust, astronomers can gain a deeper understanding of the life cycle of galaxies and the interplay between stars, gas, and dust. The role of supermassive black holes in the early universe is another important aspect that the CIB can help illuminate. Supermassive black holes are thought to exist at the centers of most galaxies, including the ones in the distant past. These black holes are believed to have played a significant role in shaping the growth of galaxies, as their immense gravitational pull can influence the distribution of matter, and energy within a galaxy. The CIB may offer clues about the earliest supermassive black holes, including when they first formed and how they influenced the evolution of their host galaxies. By studying the faint glow from ancient galaxies, we can uncover the processes that allowed these monstrous black holes to grow so rapidly and exert such a powerful influence over their surroundings. As we consider the broader implications of the CIB, it's important to remember that this radiation is not just a relic of the past, it's also an ongoing process. While the early universe was filled with intense star formation and reionization, the universe today continues to be a dynamic and evolving place. The CIB provides a snapshot of the universe's past, but it also gives us insights into the present and future. By observing the CIB in different regions of space, astronomers can study how galaxies are still forming and evolving in the present day. This can help us understand the long-term evolution of galaxies and the ultimate fate of the universe itself. One of the most exciting aspects of CIB research is its potential to reveal the existence of exotic cosmic phenomena that we have not yet fully explored. For instance, the CIB may contain subtle traces of the first black hole mergers, the birth of new galaxy clusters, or even the interactions between dark matter and visible matter. These hidden signals could provide a wealth of new information about the universe's evolution and the forces that shape it. As observational technology advances, we may soon be able to detect these faint signals and unlock even more secrets about the early universe. In addition to its theoretical importance, the study of the CIB has profound implications for our search for extraterrestrial life. If we can trace the conditions under which stars and planets formed in the early universe, we might be able to identify similar conditions elsewhere in the cosmos. The study of the CIB may eventually allow us to pinpoint regions of space where the building blocks of life could exist, or where life may have arisen in the distant past. By combining the study of the CIB with other techniques, such as the search for exoplanets, we can begin to develop a more complete picture of the conditions necessary for life to thrive. Looking ahead, the future of CIB research is incredibly exciting. As our technology advances, we can expect even greater breakthroughs in our understanding of the universe. The launch of next-generation telescopes, such as the James Webb Space Telescope, will allow us to peer even deeper into the universe's past, revealing new details about the early galaxies, stars, and black holes that shape the cosmos. With more precise measurements and improved data analysis techniques, we will be able to reconstruct the history of the universe with unprecedented accuracy. As we continue to probe the faint glow of the cosmic infrared background, we will uncover new mysteries, challenge existing theories, and push the boundaries of our understanding of the cosmos. The CIB is, in many ways, a cosmic fingerprint, a record of the universe's most fundamental processes and events. It provides us with an opportunity to study the first light emitted by stars and galaxies, allowing us to piece together the story of the universe's earliest moments. As we continue to explore this faint glow, we will uncover more about the birth and evolution of galaxies, the role of dark matter and dark energy, and the ultimate fate of the universe. The study of the cosmic infrared background is not just about understanding the past, it's also about gaining insights into the future, helping us answer some of the most profound questions about the nature of the universe and our place within it. As new technologies and observational techniques emerge, our understanding of the CIB will only deepen, revealing even more about the cosmic processes that shape the universe. With each discovery, we come closer to understanding the true nature of the universe and the forces that govern it. The mysteries of the cosmos are vast, but the study of the cosmic infrared background offers a glimpse into the deepest, most fundamental aspects of reality. And as we continue to explore these faint traces of light, we may soon find ourselves on the verge of uncovering some of the greatest mysteries the universe has to offer. As we continue to explore the profound implications of the cosmic infrared background (CIB), we begin to realize its connection to some of the universe's most fundamental forces. The faint infrared light that pervades the cosmos is not merely an afterthought or an insignificant detail. It is a critical piece of the cosmic puzzle. In fact, it is the light of stars and galaxies that have long since faded, but whose legacy continues to impact the universe in profound ways. Understanding the CIB means delving into the very heart of cosmic history and piecing together the tapestry of creation that formed the universe we know today. One of the most intriguing aspects of studying the CIB is the fact that this radiation is a cosmic relic, a remnant of a time long past. The early universe was a very different place from the one we observe today. The universe was much younger, hotter, and denser, filled with clouds of gas and particles that would eventually form the stars and galaxies we see today. The first stars and galaxies, often referred to as population 3 stars, were massive, hot, and short-lived. They emitted intense radiation, ionizing their surroundings and leaving an imprint on the universe's fabric. The light from these first stars, though faint and diffuse today, can still be detected as part of the CIB, offering us a glimpse into an era we can barely comprehend. The study of this radiation, while seemingly obscure, provides an invaluable tool for cosmologists who seek to understand the early formation of structures in the universe. The CIB is not simply a collection of scattered light. It is a map of how galaxies and stars formed and interacted in the universe's infancy. This faint glow, emitted by ancient star-forming regions, tells us about the dynamics of early galaxy formation, how galaxies assembled themselves from smaller building blocks, how they merged, and how they evolved over time. One of the most exciting aspects of studying the CIB is that it allows scientists to peer into the universe's most distant corners, observing galaxies that are billions of light years away. By detecting the faint glow of infrared light, we can infer the properties of galaxies that existed shortly after the Big Bang. This helps us paint a picture of the universe as it was when it was in its infancy, revealing the processes that took place long before we even had a chance to observe them. The radiation we detect today has traveled through the universe for billions of years, providing us with a snapshot of cosmic history as it unfolded. The CIB is also closely tied to the concept of cosmic evolution. Just as we observe galaxies today, each one unique in its own right, the ancient galaxies that contributed to the CIB were also shaped by their environments, their interactions with other galaxies, and their local conditions. Over time, these galaxies evolved, giving rise to the galaxies we observe today. The CIB is, in essence, the accumulated energy from all the star formation that occurred in the early universe. By analyzing this energy, we can uncover the ways in which the early universe transitioned from a uniform mass of hydrogen and helium gas into the richly diverse array of galaxies, stars, and cosmic structures we see today. One of the most profound implications of the CIB is its potential to shed light on dark matter and dark energy, two of the most mysterious and enigmatic forces in the universe. Dark matter, which makes up about 27% of the universe's total mass energy content, cannot be seen directly, but its gravitational effects on visible matter are detectable. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, remains a mystery. The study of the CIB may offer indirect evidence of the influence of dark matter and dark energy, as these unseen forces can affect the distribution and properties of galaxies and other cosmic structures. By analyzing the CIB's patterns, researchers may be able to better understand the role these invisible forces play in shaping the universe. At the same time, the CIB provides us with clues about the future of the universe. While it serves as a window into the past, it also offers insights into how the universe will continue to evolve. The study of the CIB's cosmological redshift, the stretching of light as it travels across the expanding universe, can reveal information about the rate of cosmic expansion, the fate of galaxies, and the ultimate evolution of the universe. As the universe continues to expand, the CIB will continue to evolve, offering future generations of astronomers new opportunities to study the cosmos. Furthermore, the study of the CIB intersects with other fascinating areas of research, such as the study of cosmic voids. These vast, empty regions of space, which contain very few galaxies or stars, are the opposite of the dense clusters of galaxies we see in other parts of the universe. Despite their emptiness, cosmic voids play a crucial role in the structure and evolution of the universe. The CIB provides insights into these voids by showing us how radiation from distant stars and galaxies interacts with the sparse matter in these regions. By studying the CIB in relation to cosmic voids, scientists can better understand the large-scale structure of the universe and the distribution of matter throughout it. Additionally, the CIB has significant implications for the study of high redshift galaxies. These are galaxies that formed shortly after the Big Bang and are so distant that their light has been stretched into the infrared part of the spectrum. These galaxies, often referred to as primeval galaxies, are some of the most important targets for astronomers trying to understand the early universe. By studying the CIB, we can identify the faint glow of these distant galaxies and begin to piece together their properties, including their size, age, and star formation rate. This, in turn, can help us understand how galaxies like the Milky Way formed and evolved over time. The ability to detect and study the CIB also opens the door to a deeper understanding of star formation rates in the early universe. The CIB is directly related to the total amount of light emitted by stars over cosmic time. By studying the CIB, we can estimate the rate at which stars were forming during different periods in the universe's history. This helps us understand how quickly the first galaxies were able to form stars and how these stars contributed to the overall evolution of the universe. As we look toward the future, the study of the CIB is only going to become more exciting. With the advent of more advanced telescopes, such as the James Webb Space Telescope, JWST, scientists will be able to peer deeper into the universe's past, detecting the faintest traces of radiation from the earliest galaxies and stars. The JWST, which is specifically designed to study infrared light, will be able to provide unprecedented views of the CIB and the first stars and galaxies that emitted it. This will allow us to trace the history of the universe with greater detail and accuracy than ever before, offering answers to questions that have long eluded us. Through the study of the CIB, we are not only learning about the past, but also shaping the future of cosmology. By investigating the faint radiation that pervades the universe, we are uncovering the secrets of galaxy formation, star evolution, and the mysterious forces that govern the cosmos. The CIB serves as a cosmic archive, preserving the light of stars that have long since burned out, allowing us to glimpse the universe as it once was and to better understand the forces that continue to shape its evolution. The study of this ancient radiation is an ongoing journey, one that will continue to reveal the hidden truths of the cosmos for generations to come. The discovery and study of the cosmic infrared background (CIB) has opened up new avenues for understanding the fundamental mechanisms behind the formation of galaxies, the life cycles of stars, and the overall evolution of the universe. What we see in the infrared is a rich tapestry of cosmic history, with faint traces of light revealing the invisible universe that existed long before human eyes could perceive it. Each fragment of this cosmic glow serves as a delicate breadcrumb, pointing the way to a deeper understanding of the universe's past and future. One of the key elements in studying the CIB is its ability to reveal the properties of early star-forming regions. These regions, often referred to as cosmic nurseries, were where the first stars were born. The light emitted from these primordial stars, though faint and redshifted to the infrared, still holds critical information about how they shaped the universe. The CIB provides a snapshot of this process, offering insight into the ways in which gas clouds collapse to form stars, and how those stars in turn influence their surroundings. The light that we observe as part of the CIB comes from galaxies that existed at a time when the universe was still in its early stages of formation. These galaxies were filled with intense star formation, and the radiation they emitted has since been stretched by the expanding universe, shifting it into the infrared part of the electromagnetic spectrum. This process, known as cosmic redshift, is one of the most important phenomena in cosmology. It allows us to look back in time and observe events that occurred billions of years ago. The study of the CIB is crucial because it helps us piece together the timeline of galaxy evolution. It tells us about the rates at which galaxies were forming stars, and how that process changed over time. For example, astronomers have been able to use the CIB to identify periods in cosmic history when the rate of star formation was particularly high, such as during the cosmic dawn when the first galaxies were forming. These discoveries offer critical clues about the conditions necessary for galaxy formation and star birth, and how the physical environment in the early universe contributed to the overall shaping of cosmic structures. Another fascinating aspect of the CIB is its role in helping us understand the processes of reionization, the period in the early universe when the first stars and galaxies began emitting enough radiation to ionize the hydrogen gas that permeated space. This process is thought to have taken place between 400,000 and 1 billion years after the Big Bang. The CIB provides indirect evidence of this crucial phase in cosmic history, as the light from early stars and galaxies would have played a significant role in this process. The light emitted by population 3 stars, the first stars formed from primordial elements like hydrogen and helium, is believed to have contributed significantly to the CIB. These stars were much more massive and hotter than the stars we see today, and they emitted vast amounts of ultraviolet radiation that ionized the surrounding gas. The faint infrared radiation we detect today, a remnant of this process, is a powerful tool for studying the properties of these stars, including their mass, temperature, and lifespan. By studying the CIB, we can also gain insights into the formation of supermassive black holes. These enigmatic objects are thought to have formed early in the universe's history and played a key role in shaping the growth of galaxies. Supermassive black holes can affect the star formation process in their host galaxies, and the radiation emitted by these black holes can contribute to the CIB. Understanding how supermassive black holes form and evolve over time is a key goal for modern cosmology, and the CIB serves as a valuable piece of the puzzle. A significant challenge in studying the CIB lies in the fact that it is often faint and easily obscured by other sources of light. The Milky Way galaxy itself emits a significant amount of infrared radiation, making it difficult to isolate the faint signals coming from distant galaxies. However, advanced telescopes like the Spitzer Space Telescope and the Herschel Space Observatory have made it possible to observe the CIB with greater sensitivity and precision. In the near future, the James Webb Space Telescope, JWST, is expected to provide even more detailed observations, offering a clearer view of the distant universe and the CIB. The potential for future discoveries through the study of the CIB is vast. As we continue to push the boundaries of our observational capabilities, we will be able to detect even fainter traces of light and explore deeper into the history of the universe. The CIB serves as a bridge between the present and the past, allowing us to observe the processes that occurred in the earliest stages of the universe and uncover the mysteries of how galaxies, stars, and other cosmic structures formed. Furthermore, the CIB is not just a tool for studying distant galaxies. It is also a way to understand the physical conditions of the universe as a whole. For example, it can reveal information about the intergalactic medium, the sparse gas that exists between galaxies. This gas is mostly hydrogen and helium, and it plays a crucial role in the formation of galaxies and stars. By studying the way the CIB interacts with this gas, we can gain a better understanding of the large-scale structure of the universe and how matter is distributed throughout it. In addition to helping us understand the early universe, the CIB also has the potential to provide clues about the future. As the universe continues to expand, the CIB will evolve, just as it has over billions of years. The study of this radiation allows us to probe the future expansion of the universe and understand how cosmic structures might evolve in the coming eons. As galaxies continue to move apart due to the expansion of the universe, the CIB will become even more redshifted, and its intensity will decrease. Observing these changes could provide insights into the ultimate fate of the universe, including theories about the Big Freeze or even the possibility of a Big Crunch. One of the most exciting prospects of studying the CIB is its connection to the phenomenon of gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, like a galaxy or cluster of galaxies, distorts the light from a more distant object, magnifying and bending it. The CIB is often affected by this process, providing a unique opportunity to study both the distant galaxies that emitted the radiation and the intervening structures that distorted the light. This can offer a wealth of information about the distribution of matter in the universe, including both visible and dark matter. The study of the CIB has profound implications not just for our understanding of the past, but also for the future of cosmology. As we continue to refine our observational techniques and develop new tools for studying the universe, we will be able to gather more detailed information about the early universe, galaxy formation, and the role of dark matter and dark energy. The CIB will continue to serve as a critical tool for unlocking the secrets of the cosmos and revealing the forces that have shaped the universe since its inception. By studying the CIB, we are not merely observing the universe. We are engaging in a profound act of cosmic discovery. We are looking at the universe through the lens of time itself, peeling back the layers of cosmic history to reveal the forces that shape the stars, galaxies, and structures that populate our universe today. The faint glow of the CIB is more than just light, it's a link to the distant past, a bridge to understanding the birth of the universe and the forces that continue to shape it. The cosmic infrared background offers us a glimpse into the distant past and a glimpse into the future of the universe. It is a cosmic relic, a remnant of the first stars and galaxies that formed after the Big Bang, and a vital piece of the puzzle that will help us understand the origins of our universe and the forces that continue to influence it today. Through its study, we are gaining new insights into the formation of galaxies, the birth of stars, and the mysteries of dark matter and dark energy. The CIB is not just an afterthought, it is the key to unlocking some of the most profound mysteries of the cosmos. The cosmic infrared background, CIB, continues to reveal more secrets about the universe with each discovery. As we explore the faint glow left behind from early star formation, we not only deepen our understanding of the origins of galaxies, stars, and black holes, but we also begin to connect the dots that link the birth of the universe to its present state. The potential of the CIB as a tool for cosmology is far from exhausted. The data collected so far is just the beginning, and new technologies and missions promise to provide ever clearer pictures of the distant past and future of our universe. A particularly exciting aspect of CIB studies is its relationship with dark matter and dark energy, two of the most mysterious forces in the universe. These invisible entities affect the universe on large scales, yet their properties remain largely unknown. The CIB may hold clues that help us uncover the nature of both dark matter and dark energy. For example, the way the CIB interacts with the intergalactic medium, the gas between galaxies, can provide insights into the composition of the matter that fills this space, including potential clues about dark matter. Some scientists have proposed that the CIB might even provide a way to detect the signature of dark matter itself. The idea is that dark matter could be interacting with the normal matter in galaxies in ways that would leave an imprint on the CIB. If we can detect these tiny effects, it might be possible to learn more about the properties of dark matter, including whether it interacts with light and other forms of radiation. This is still a speculative idea, but the implications are vast. A direct detection of dark matter through its interaction with the CIB would revolutionize our understanding of the universe. Furthermore, by analyzing the CIB, astronomers can gain more information about the formation of galaxies. Galaxies didn't appear all at once. Instead, they formed over billions of years, evolving through a complex series of processes that shape their structure and composition. The CIB provides a window into the very early stages of this process, helping us understand the types of galaxies that existed in the universe's infancy. By studying these ancient galaxies, we can learn about the conditions that allowed them to form, including the role of gas, dust, and dark matter in the process. The CIB also offers valuable information about the environment in which these galaxies existed. During the early stages of galaxy formation, the universe was filled with a hot, dense gas. This gas, which was mostly hydrogen and helium, was eventually cooled by the radiation from stars and galaxies, allowing the formation of galaxies and stars to take place. The study of the CIB helps us understand how this process occurred, and how the first galaxies and stars were able to form in a seemingly inhospitable environment. Understanding these early stages of galaxy formation is crucial for understanding how galaxies evolve over time, and how the large-scale structures of the universe came into existence. The study of the CIB also ties into the ongoing search for the earliest signs of life beyond Earth. By understanding the conditions under which stars and galaxies formed, we are better equipped to identify the potential for life on planets orbiting other stars. If we can understand how life emerged on Earth, we might be able to identify similar conditions elsewhere in the universe. The CIB is one of the key tools we have for studying the conditions in the early universe, and its findings could help guide future missions to search for life beyond Earth. As we peer deeper into the universe's past, the CIB offers us a glimpse into an era of cosmic history that is otherwise hidden from our view. The light that we detect from the CIB is a relic of the distant past, a faint echo of a time when stars and galaxies were first beginning to take shape. This radiation carries with it information about the universe's birth, its earliest stars and galaxies, and the processes that shaped them. By studying the CIB, we are not only learning about the distant past, we are also uncovering clues that will help us understand the future evolution of the universe. As our technological capabilities continue to improve, we can expect the study of the CIB to yield even more exciting discoveries. With the launch of next-generation telescopes, such as the James Webb Space Telescope, we will be able to observe the CIB with unprecedented detail and precision. This will allow us to look even further back in time, into the era when the first stars and galaxies were just beginning to form. These observations will give us a clearer picture of the conditions in the early universe, and will help us refine our models of galaxy formation and evolution. Additionally, the study of the CIB may offer insights into some of the universe's more enigmatic phenomena, such as the mysterious cosmic voids and the large-scale structure of the universe. Cosmic voids are vast expanses of space that contain very little matter, and they have been a subject of great interest for cosmologists. By examining how the CIB interacts with the matter in these voids, we can learn more about the distribution of matter in the universe, and the forces that shape its evolution. The CIB is not just a tool for understanding the past. It also has the potential to shed light on some of the most profound questions about the universe's future. The study of the CIB could provide clues about the ultimate fate of the universe. Will the expansion of the universe continue forever, or will it slow down and eventually contract? Will the universe end in a big freeze, a big crunch, or some other scenario entirely? By analyzing the CIB, scientists hope to gain a deeper understanding of these questions and more. In conclusion, the cosmic infrared background is one of the most fascinating and promising tools in modern cosmology. It provides us with a unique window into the early universe, revealing the processes that led to the formation of galaxies, stars, and other cosmic structures. Through its study, we are learning more about the history of the universe and the forces that have shaped it over billions of years. The CIB holds the potential to unlock many of the mysteries that still surround the formation and evolution of the cosmos, from the birth of the first stars to the distribution of dark matter and dark energy. As our observational techniques continue to improve, the CIB will undoubtedly play a crucial role in deepening our understanding of the universe, both past and future. The future of CIB research looks incredibly bright, with the advent of new telescopes and advancements in observational techniques. As we continue to study this cosmic relic, we will unlock even more secrets about the universe's earliest moments. The CIB is not just a fascinating relic of the past, it is also a key to understanding the future of our universe, and will undoubtedly continue to captivate the imaginations of scientists and cosmologists for generations to come. The faint, distant glow of the CIB is a reminder that there is still so much more to learn, and that the universe has many more secrets waiting to be discovered. As we gaze into the depths of space, the CIB will remain one of our most powerful tools for uncovering the mysteries of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.